Chodziła z mikrofonem przy pytaniach, tak? Proszę? Hello everyone, good morning on this beautiful Wednesday. My name is Barbara Piętka and I'm from the University of Warsaw and I have a great pleasure to chair the session. But before we start, we have a small announcement. Aniu, would you like to say?
Thank you very much. I think you already noticed, but we have an announcement that today we will have a conference photo. So we ask you to, after the next session, so at 12:45 we should finish the session, and then we ask everyone to go to the entrance to the hotel beside this clock, and there we will take the pictures. So please remember about this. Thank you very much.
Thank you so much. So the first talk will be given by David Snoke from the University of Pittsburgh, and he will be talking about the exciton polaritons, polariton condensates, and gallium arsenide substrate materials over a wide range of territories. Please, David, the floor is yours. Welcome.
Okay, so welcome 9 o'clock in the morning, and I hear that for some people, maybe they didn't get to bed until a few hours ago. So if so, thank you for making it out to the talk. A couple things before I start in on the talk. First of all, a lot of the credit, let's see here, am I doing something wrong here? Does it need to be turned on? It's just, we need to slide. Okay, here we go. A lot of the credit goes to my graduate students and postdocs. I also want to specifically talk and give credit to two growers, one of whom is in the room. I'm not really going to talk a lot about the story of the fabrication and the growth of these MBE structures, but it's a huge part of the story of just the quality of the samples. When you get better quality, you get qualitatively different physics in a lot of cases. The other thing I just want to note, very sadly, okay, it's still not, oh, there we go, okay. Some of you may be young and not know who Peter Littlewood was, but he just passed away yesterday, actually, and is a real sad thing for the field. He trained up a generation of theorists who had a huge impact in this field, and many of us knew him well. And he was a wonderful person, so I just really want to note his passing with sadness. I've already at this conference, a number of speakers have started out by giving their conclusions. So I think I'm going to stick with that pattern. So here are three general conclusions from my talk that I'll try to justify. So the first is that you sometimes will hear in the field of polaritons that polaritons are an intrinsically non-equilibrium system. That's simply not true. They can move from equilibrium to non-equilibrium, it depends, okay? And so this is often a lore which is out there, and it's simply not true. It just is a matter of the lifetime of the samples. And so again, with the quality of the samples that we're getting in gallium arsenide, we can reach a true equilibrium. Another thing that I'll talk about is that several people have talked about the coherence of a polariton condensate. Coherence and superfluidity are related, but are two different things. And polaritons can become a superfluid, and I'll talk about that. And then lastly, another sort of counterintuitive thing, which is in the title of my talk, which is there's often an assumption that you can only have polaritons at temperatures that are less than the exciton binding energy, and that also is not true. You can have polaritons at temperatures where KT is well above the exciton binding energy. Maybe that's also surprising. All right, so one of the advantages of coming in the middle of the week is we've already had lots of talks talking about polaritons, so I don't need to introduce them at any great length. Just for some of you who may have arrived recently, the whole trick is basically just to mix typically excitonic states with photon states. So the structure that we're typically looking at for the experiments I'm going to talk about is a vertical cavity. So you have two dielectric stacks. In our case, those are also going to be alloys of gallium arsenide and aluminum arsenide. And then that makes a mirror with a cavity. And then we put active quantum wells inside the cavity at the antinodes of the confined mode. And that's going to lead then to a coupling, which will give you then a mixing of the exciton and the photon states. And if you just do standard quantum mechanics, you see that the mixed states are now a superposition of being partly photon and partly exciton. And that's basically the whole trick for getting polaritons. I'm not sure what I should point this at here. Okay. So one of the things I want to point out here, though, is that what's necessary for the polariton effect is simply that we have a sharp resonance. It does not have to be a stable exciton. You don't have to have an electron and a hole find each other in the system first, become an exciton, and only after that become a polariton. The fact is that all you need for the polariton effect is any sharp optical resonance. And as long as it mixes with a photon, you'll get the polariton effect. So that will come up later. So one of the reasons why we do this polariton trick is because you get this light effective mass. So you can see that the mass of the particles in this lower polariton branch really is inherited from the effective photon mass in the cavity and is not really related to the exciton mass, which is much, much greater. So the effective mass here is about 10 to the minus 3 electron masses. So it's very, very light. And that matters because the critical temperature for Bose condensation, if you just do sort of unit analysis, quantum effects become important when the distance between the particles is comparable to their de Broglie wavelength. And so the de Broglie wavelength depends on their temperature and also their mass, and then their density gives the distance between them. And so if you just rearrange the units, you get that the critical temperature for quantum effects to be important depends on the density, but it goes inversely with the mass. So that means that you get high TC automatically if you have very light mass. And so the typical mass of these particles is much, much less than an electron mass. And so it's very normal to expect a very high temperature condensation. So another thing just to orient, speakers have talked about this, but in a typical sort of cold atom experiment, you might think of a TC where you're coming at fixed density and dropping down below some critical temperature. In most of the experiments that I'm going to talk about, we're going to be crossing the boundary the other way. So we're going to sit at fixed temperature, and then we can talk about a critical density that you go above in order to get the condensation. Okay, so just a little bit more background on the experiments. This has been mentioned by several previous speakers, but the emission of the photon, so even though this is a very high Q cavity, we always get some leakage of the photons coming out, and that is our data. That's what we're going to look at, and you essentially have a one-to-one mapping that a polariton that's existing in this two-dimensional plane has some small chance of turning into a photon that escapes, and then the angle of that photon will directly tell us the momentum of the particle. And so we get automatically from our data, we can switch between real space imaging and momentum space imaging just by basically going near field or far field in our optics experiments. And so we can just directly in situ image the momentum space and the real space. Now, another thing, which maybe is a little less familiar, is that the same rule applies the opposite way. So if we come in with a laser at a given angle, we can resonantly pick any one of these states down here in the lower polariton, and so we can inject particles with a given momentum as well. And so here's a cute experiment from a few years ago. Has nothing to do with condensation. It just really tells you about the quality of these samples. So here we're injecting resonantly, as I showed, at some angle, and that's going to create polaritons that are propagating now in this planar cavity. But there's going to be a wedge in the cavity. And so if we think about this by analogy, the polaritons have an effective mass, so they look like little particles with mass. The wedge creates a gradient of potential energy, just because there's higher energy when the cavity has shorter wavelength over here. And so if we inject them this way, we have essentially a ballistics problem. There's going to be a trade-off between kinetic energy and potential energy. If you've done freshman physics, you know what the answer is, right? So the ball rolls up, loses all its kinetic energy, turns around, and goes back the other way. All right, so that's the setup. This is the actual data here. So we're using time-resolved imaging with a street camera, and this is just a parabola, right? So we're injected, and as time goes on, they simply turn around and go back the other way. So this is ballistic motion in a cavity. But there's a lot of sort of neat things to point out about this. So one of them is, it's an optics effect. It's very weird. You're basically saying that you fired light in this way, and it just slows down, turns around, comes back at you again. So it's not hitting any interface. It's just trade-off of kinetic and potential energy. It reverses and comes back at you. So in one way, you could say this is the slowest light in the world, right? Because at one point it reaches zero, right? And turns around and comes back the other way. The other thing is it says a lot about the quality of these samples. So if you look at the distances here, this is in millimeters, okay? So this thing has traveled about 2 millimeters before it gets to the place where we're looking. And then we can actually just take the intensity as a function of time and read off of that a lifetime of, for the polaritons. And in this case, it's about 200 picoseconds. So that, again, just tells you this, just ballistic transport, you can get enormous distances in these high-quality, high Q. So this corresponds to a Q of about 400,000 for the cavity. All right, so let's talk about condensation first in our low-temperature experiments. So both condensation of polaritons has been seen in one form or another since about 2006, 2007. And there was a number of groups that reported it around the same time. So I'm going to tell you about some recent experiments. And it turns out one of the easiest, best ways to make a nice homogeneous condensate is simply to take a large laser spot, defocus it, and then only look in the middle. And then it's very, very homogeneous, and it essentially looks like a uniform two-dimensional gas in that region. And so you can then start to do two-dimensional Bose physics in that regime. Here is some examples of data. So now we're analyzing a K-space. As I said, this is simply looking at the angle distribution of the emission. And so this is a typical PL spectrum as a function of angle. And you can see this is that lower polariton with an effective mass, which is a parabola. And now if we take slices through this in the vertical direction, we get spectra that look like this. And if we integrate under this curve, we simply get the occupation number of the particles at a given momentum. So we're getting the momentum distribution directly from this. We had an early paper that I collaborated with Keith Nelson's group a few years ago. This is more recent data. And you can see now what we're doing is we're plotting now the extracted occupation number as a function of kinetic energy. And I want to emphasize there's not a free fitting parameter in the vertical direction, right? So these are extracted absolute numbers, all right, for the actual occupation number. And so to do that, you have to know your photon counting efficiency, and also you have to use the same efficiency factor for all the curves as you turn up the density. You can't individually separately fit them, right? You have to fit the whole set of curves with one theory. So if you look at the fit function, It's the Bose-Einstein distribution, and there's no factor out front for an overall fudge factor. This mu, the chemical potential, gives both the curvature and the absolute value of these, all right? And so now these are near perfect fits to the Bose-Einstein equilibrium distribution. And you can see our ground state occupation, in this case, is about 100. I think he's pushed it up to 500 or even close to 1,000. So you notice this is an equilibrium distribution. So this is one of my first take-home messages, is that the condition for equilibrium for any system is that the scattering time, the thermalization time, be fast compared to the time they spend in the system. And so a typical scattering thermalization time for polaritons at these densities is some tens of picoseconds. So if your lifetime is less than 10 picoseconds, you're not going to reach a full equilibrium. If your lifetime is 200 to 300 picoseconds, then you can reach a very good equilibrium, as we see here. And so this is no different from cold atoms, right? Cold atoms have a lifetime to leave the system. They can tunnel out of the trap, they can evaporate. So cold atoms are no different from this in that they can escape the trap just as our photons can escape the trap. And so you can move away from equilibrium in these systems, but if you have a long enough cavity lifetime, you can reach a true equilibrium. Okay, so this is just sort of typical data. I'm talking about coherence. So this is now looking at several of these as we increase the power. And there's a lot of things going on. Some other speakers have mentioned this. So you see, first of all, a broadening of the line due to the decoherence that's going on as they increase their density. But then when they reach condensation, it becomes spectrally narrow. So if I take a cut in the vertical direction, I get the spectral width. And so you can see it first broadens and then narrows again when you reach BEC. The other thing you can see very clearly is a Ballou shift, and other speakers have mentioned that's due to the repulsion between the particles. So you have an overall shift of the chemical potential due to the interactions between them. But this line width now is an indirect indicator of the coherence in the system, but we can do better than that. We can do a direct interferometry experiment to look at the coherence. There's a lot of things you can learn from that. So in this experiment, we're going to image the sample, and we're going to do it in K-space in this particular experiment. We'll send the image through two legs of a Michelson, and one of them we're going to flip left-right. So we're going to get self-interference, and that will tell us about the correlation length of the coherence in the system. So here are some typical pictures that we would get. This is again in K-space. So we see below threshold when we don't have a condensate, you see a little bit of residual coherence, which is really just the same as you would see if you did a Michelson with a white light bulb, right? You probably, as a student, as an undergrad, maybe did an experiment where you could get fringes just from a white light bulb, right? So, but now if we increase the density, we see the coherence increasing until above threshold we have nearly fully coherent system. So we can analyze this quantitatively and get what one could call a coherent fraction. This is sort of analogous to a condensate fraction, but in a two-dimensional system, the condensate is actually not well defined. You never have a macroscopic condensate in just the k equals 0 state, right, in 2 dimensions. And so the coherent fraction is sort of playing an analogous role for us here. So you can see there's an incoherent part and a coherent part, and we can simply extract these from the data. And if we do that, we get plots that look like this. And there's a lot going on here, so I'll try to go through this carefully. So the solid dots are our data where we've extracted the coherent fraction. And you can see that it increases according to this power law, and then of course, well above the critical threshold, you get nearly 100%, but we never see exactly 100% fringe visibility. Now, another thing that's interesting that's going on is the critical density is this purple line here. And you can see that that critical density is basically the coastal thallus normal to superfluid transition. But there's no sharp jump of the coherent fraction at that point. So what's happening there at that threshold is not that the coherent fraction is jumping up, but something is happening to the power law, okay? So if you look at this plot here, this is simulations done numerically, just using a Gross-Pitievsky equation. And notice, by the way, in this equation, there are no terms for generation and decay, right? This is just a straight old, Gross-Pitievsky equation. And this figure here generates the triangles, all right, from the numerics, okay? And we see we get a very good fit to the actual data, assuming no generation and decay. But now if you look at this result, what you see is as we increase the density well below the critical threshold, we see exponential decay in real space of the correlation function. Well above it, you see power law decay, and there's a separation right at some critical threshold, and that is the coastal thallus transition. And so you could say the transition comes from the transition between exponential decay and power law decay, and there's some sharp threshold, which means that vortices will be stable below here, but vortices don't like, they basically, you reject turbulence when you're up in this region here. But the overall coherence length, you can see, is not having a sharp jump. It's just, if I took the integral under this, I would basically get these dots here. And so you can see that the coherent fraction increases continuously, even while the correlation function has a sharp jump in its behavior from exponential to power law decay. So we learn a lot of interesting things from this. And I'll mention that Peter Littlewood and a student did a fair amount of analysis of this, and there's a paper in the archive that looked at this in some detail. All right, now, another set of experiments which is underway at present is very nice. I remember talking to someone just in the past year, and I was making this point about how there is really no fundamental difference between polaritons and cold atoms in terms of non-equilibrium. And this person said, oh no, that's not true, because with polaritons, the laser always has to be on. And if the laser is off, you don't get a condensate. That is not true, okay? So this is an analogy of a quench. So this is now a time-resolved experiment in which you have a very short laser pulse, and now we're looking at the spectrum as a function of time. And you see at low power, when you don't have a condensate, at 0 time, you have this laser pulse that hits it, and you just have a broad distribution, then that cools down until it reaches the lattice temperature, and that's pretty much what happens. In the case of the condensate, this 70 milliwatts is right around the critical threshold for condensation, and this is well above the threshold for condensation. And you can see that you have now a spectral line narrowing. All right, so the laser is only on right at 0, plus or minus, say 5 picoseconds. And then at all these later times, the laser is off. All right, there's no laser pumping at that point. You just have this hot gas which is cooling down. And so now we can analyze this quantitatively. And so this is a little bit busy, so let me talk about this again. So you see, first of all, the intensity is the red, so there's a big peak, and then that's dropping down. That's this red plot here. There's a big blue shift. Again, the density is giving a shift of the energy. But the one I want you to focus on is the green curve. Or the green curve is the width of the line as a function of time. So at first, you hit it with this laser, you get something very hot and very inhomogeneous. And so you have this big line width. But now, 100, 150 picoseconds after the laser pulse is off, you see that the line gets very narrow, okay? And this is red on this, so this is less than 50 microeV. It's about 30 or 40 micro electron volts in width, all right? And then actually it broadens later. So what's going on at late times, it's simply an incoherent cold gas, all right? Which is narrow because it's cold, all right? But here at this intermediate time, it's actually hotter but narrower, all right? And that's because of the quantum statistics. It's become coherent. But that has happened 100 picoseconds after the laser was turned off, all right? So it's truly just the quantum statistics of the particles themselves. Okay, so from the same set of experiments, you can do time-resolved interferometry. So this is the same interference type measurement that I showed before, but now done in a time-resolved way. And you see at early times, you have just a very short coherence length where you can see those fringes. And the coherence length is increasing again in time. So it's getting less dense, but also colder. And so actually the condensate fraction, so to speak, is the largest at this point, all right? Well, so the laser again is at 0. You have a hot gas that's cooling down, is recombining, but eventually you see the coherence length is a maximum here, and then at later times, it becomes a cold, incoherent gas, and the coherence length shortens up again, all right? And so you can see that at late times. So here, this is a plot. It's a little tricky to figure out here. Okay, so the color bar is for the color of the different curves, and you can see the early time one is this one here, which has this exponential decay in real space, all right? So that is not coherent. That's a slice at this time here, okay? On the other hand, at intermediate times, around 150 to 200 picoseconds, all right, you're looking at these guys here where you can see you have this fit to a power law type behavior. So for instance, this red curve, which is right around here, you can see that's right around where I drew this line, right? And you can see a very nice power law behavior. Yeah, actually the red right here, this is the best. You can see a very nice long power law behavior. Of course, it doesn't last forever because it's a finite size spot. So it can't go to infinity because the thing is only 10 or I think it's about 40 microns across. Okay. So now, that's just all sort of talking about equilibrium, two-dimensional Bose behavior. Now we can do some fun stuff. So one of the things you can do, I don't know if people have talked about this too much, but you can use a spatial light modulator to create a cloud of excitons that creates a potential energy profile. So in this experiment, we're using a spatial light modulator to create a ring with a pillar in the middle. And so this is a ring trap. So as seen by the polaritons, they see a ring trap where they're confined to circulate inside of a ring. If you have questions about how that's done, we can come back to that. But now let me remind you of some condensate physics here. So in general, if I have a condensate, I describe it with an order parameter, which has an amplitude and a phase. And if I go around any closed path inside of that condensate, I have to come back to where I started. So that means that the phase has to wind by 2 pi. So that means then, since the velocity in a condensate is given by the gradient of the phase, that means that there's quantized circulation. It can't just circulate at any old velocity. It can only circulate at quantized velocities where the phase winding is some multiple of 2 pi. And so this is called, quantized circulation. And this is what's responsible for flux quanta in a superconductor, and it's also what's responsible for quantized vorticity in superfluid helium. In the experiment, we have a ring condensate with roughly equal density around it. So this is all just theory here. We can now imprint on it a phase winding of 2 pi and then predict what the interference pattern will be for this left-right interference. And so in this case, now we're doing it in real space. So we're interfering one side of the ring with the opposite side of the ring. Now, this is what our simulated data is. This is what our data is going to look like. Now I can take this and I can use this to extract the phase winding. And the way you do that is by Fourier transforming it and erasing the vertical line spacing, and then Fourier transforming it back to real space. And so what you see in the data is you have a 2 pi phase winding because you've got 2 condensates each going 2 pi the opposite way, right? So now we have 4 pi in our phase map. All right, so that's what we see in the data. Okay, so here we've got a ring condensate. In this case, we came in with a short picosecond pulse, hit it at the top, that caused it to circulate one way. So this is the data we actually get, the interference image. This is the extracted phase map, and you can see it's winding this way. All right, so we have a 2 pi phase winding. And if we come in and kick it the opposite way, all right, then this phase map, you can see the interference fringe has extra fringes on the top, whereas here it had extra fringes on the bottom. And if we extract the phase winding, we get circulation the opposite way. So you see here it's going light to dark this way, and here it's going light to dark the opposite way. So we're extracting this quantized circulation. But now we can do this with a street camera and time resolve it. And what's really quite nice is that, here we give it this kick, essentially destroy the coherence, and then it sets up its circulation. And it's rock solid for as long as we can measure, all right? So again, it's an interesting way to think about it. We have a CW laser creating the condensate, all right? That is the background. Then we come in with a picosecond laser and hit it, all right? That picosecond laser is then stopped and is turned off. And the steady state condensate then continues to circulate forever, essentially. It doesn't stop. And this is what you can call persistent circulation. And if we count how many times does it circulate without being kicked, well, there's about 14 nanoseconds between laser pulses. So that means it's circulating about 20 times around without being pushed from one laser pulse to the next. So interestingly, the lifetime of any one polariton is only about 300 picoseconds in this experiment, but the coherence time is longer than 14 nanoseconds because the population has its own coherence, which is separate from any one particle. So the population has its own sort of existence as a steady state coherent system, even while polaritons are being generated and decaying. So one application, this is actually an older experiment, but this is something that is kind of cool about superfluids, which is that you get this long distance flow, all right? So this is an experiment in which we etched down our top mirror, and so we made a little pillar, and the strain led to low energy minima at the corners of this thing. So if you, this is now looking in real space, and the corners are the low energy points. So we took a laser and just sent a laser spot into the middle of this. And at low power, when you're not a condensate, you simply see PL where the laser was, all right? So it's just an incoherent PL from a source, not too surprising. But now as we turn up the power, boom, right at one point, the flow, they all move, the polaritons move as the superfluid to the corners. And so this is about 75 microns that they've moved, from the center to all 4 corners. That transition happens suddenly at the superfluid transition, all right? So you get a long-range motion that happens, and this is now seen in a lot of different samples, where you go above a certain density threshold, and suddenly the long-range propagation jumps up. And so we go from only diffusing a few microns to moving ballistically for 50 to 100 microns. Another interesting thing that happens that has been seen many times now is there are 4 corners. They all have slightly different energies due to the different strains. And if you track the energy of those as a function of pump power, you see at first they're at different energies. So this is, this is about half a millivolt difference in energy. At some point, though, they start to feel each other through tunneling, and they phase lock to have exactly the same energy. All right, at this point, they're one condensate extending all the way around the edge of the sample instead of being 4 separate condensates. And so at this point, we could do interferometry and actually see that that corner is coherent with that corner and that they all have the same energy together. So phase locking of 2 different condensates is something that you see in these polariton systems as well. Okay, so for the last 5-10 minutes, I guess, I'm going to talk about going to room temperature. This is funny, but this is an experiment we could have done 10 years ago, but didn't think to do. The lore was always gallium arsenide will not work for room temperature condensation. You need a special material, like a perovskite or a 2D material or something. Well, guess what? It is possible. So if we just think about the conditions for condensation, if we go to higher density, so higher temperature, we're going to need higher density. That's that relationship I gave you at the beginning of the talk. Now, there's a problem with that, which is if you increase the density too much, then you can collapse the system into just a plasma due to Pauli state filling. So you need to have the density high enough, but still avoid this limit where Pauli state filling becomes important. All right. Well, it turns out the condition is related to the Bohr radius of the excitons. And so it turns out at 300 Kelvin, you can still have this condition be satisfied that you're not in the Pauli state filling regime. On the other hand, the Pauli state filling can do other bad things, which can lead to a problem. So in general, you want to be able to keep the density as low as you can, but to do that, you have to have the lifetime be long, all right? So if you have a short lifetime cavity, you're not going to be able to see room temperature condensation in gallium arsenide. But if you have a few hundred picoseconds of lifetime, then effectively you don't have to pump as hard in order to get the condensate. So you have lower overall density in your electron states. Sometimes people say, well, how can this be? Because the binding energy of the excitons in gallium arsenide is about 10 millivolts, and KT is 25 millivolts. Well, it turns out when you hit KT, KT equal to 10, it's not like all the excitons just vanish in a puff of smoke, right? There is what's called a mass action equation, which chemists are familiar with. And so, yes, when you're at room temperature, you get a equilibrium between free electrons and holes and excitons, but there's still plenty of excitons around at room temperature. So remember I said all you need is a sharp resonance, all right? You don't need to have excitons be the only thing that's around, okay? So here, this is a really terrific, okay? This is from a Lauren Pfeiffer sample. This is with the top mirror taken off, okay? This is photoluminescence at room temperature, all right, of the excitons in gallium arsenide. And the line width, full width, is about 10 millivolts, okay? That's an outstanding number if you are familiar with quantum well physics. So what you see is that there's a perfectly good resonance there. And that can be mixed with the photon and make polaritons. That's all we need, all right? Now you also see that the upper light hole states are getting occupied as well. Okay, so why do we want strong coupling? This gets back to the very first slides I was showing. When you do this coupling between the two, I left out at the beginning the broadenings of the individual states. If you actually put those in, you get a more complicated formula. And what you see that you get is basically, instead of sharp lines, you get smeared lines. If the smearing is comparable to the gap between them, then you're in weak coupling. You basically can't distinguish between these two states. What's important about that, as a sort of a technological thing, is that when you're in strong coupling, you have strong nonlinearity. These states will shift with density quite strongly. Once you go to weak coupling, the photons are basically pinned at the cavity energy, and they don't shift strongly anymore with energy. So strong coupling, in some sense, is just a nice curiosity, but technologically, it means that you have strong nonlinearity, which is very important for any kind of optical swing type processes. All right, so let's look at some data. All right, so this is at low density, not a condensate. This is at room temperature. And you can see here just a couple different detunings. So here you can see the lower polariton and the photon mixing with it there. And so we have a very nice, clear two peaks. And in this case, the crossing is not at the center. The crossing is out at a finite angle. This is just another detuning, and this is the ripples of the mirror itself. So these are just coming from the fact that we pushed this down in detuning. But now, again, you can see here we have this very strong anti-crossing that shows strong coupling. Now, this has been seen before in some of these papers here, but when they tried to make a condensate, it went away. As they turned up the density, it went into weak coupling before they could get condensation. But now we can do this as a function of power. And so what you can see now, we're tracking the lower energy. And so I'm going to switch to calling this the middle polariton instead of the upper, because now we have to worry about three states, right? The heavy hole, the light hole, and the photon. And so when we count for all of those, what I was calling the upper polariton now gets called the middle polariton. But you can see even at condensation, where you see this big jump up in intensity, the gap between the upper and the lower polariton has been shrinking. So you see several things going on at once. You see the gap closing. That's due to this Pauli state filling. All right. You also see a blue shift of both lines due to their repulsive interaction. But the gap doesn't close to zero when you get to the condensation threshold. You still have this strong coupling gap. And so in this region, right at condensation, you see very strong nonlinear effects happening, which is, again, technologically useful. So this means that we can do coherent nonlinear shifts at room temperature in this system. Okay, so I'm over time. I'll just make a couple points here. One is the work that I just showed you was inspired by this earlier work by this group, Pizarca's group here locally, where they did this in weak coupling with photons. And in all these cases at room temperature, the actual fit temperature that you get is less than room temperature. There's actually some optical cooling going on, and I don't have time to go into that. The other thing that we can see is that in some circumstances, we can get the condensate to appear not in the bottom level, but in the top one. So you can see, well, okay, this is just showing the energies, but I think I have a better plot here. Yeah, so here you can see that we can either get the condensation in the lower polariton or in the upper so-called middle polariton, just depending on the details, right? So at 100 Kelvin, this one becomes the condensate. At 70 Kelvin, under similar conditions, the bottom branch is the condensate. So we actually mapped out a phase diagram of dozens of positions, and you can see in this regime here, this is detuning exciton fraction, this is temperature. In this case, it becomes an upper polariton condensate all the time. In this case, it becomes a lower polariton condensate. And right on this boundary, it's unstable. And I'll skip this for sake of time. But what you can see is it's actually, in some cases, popping. It can't decide whether it wants to be an upper polariton condensate or a lower polariton condensate, and so it's popping between the two. And so we have unstable jumping, telegraphing between the two types of condensate. All right, so with that, I'll finish up that we can move from equilibrium to non-equilibrium. We can compare it to equilibrium theories that it works very well with. We can see superfluid persistent circulation, and we can move. So we have not seen superfluidity at room temperature, but we have seen condensation at room temperature, including in the upper polariton state. So I'll finish with that. Thanks.
Thank you so much. So the time for discussion and the questions. So, Jesse?
I would have a silly question because about the room temperature case. It seems the quantum world is pretty wide because the light Hall and heavy Hall transitions are close to each other. So I'm wondering if this can be done also for purer case where the upper states are more separated, and how important in this case is the valence band states mixing?
Yeah, so actually, let me go back to that. There's a 70 angstrom well, so they're not really that close to each other. So if I go back to just the bare excitons, or was that here? Okay, so you can see this is 50 millivolts here, so this is about 30 millivolts splitting between those two. So it's up to 70 angstrom wells. Okay, so they look close because we're used to seeing things, at low temperature, right? But it's actually, the reason why you can see both is because the temperature is so high, right? So the second part of your question, now I forget. Yeah, that's what gives the heavy hole, light hole splitting, yeah.
Any other questions?
Thank you for the great talk. I was wondering, you showed data about the rotation, so you kick and it starts rotating.
Yeah.
But I just didn't quite see it in the data that you kick it and then it rotates. I saw kind of flat line and then...
Yeah, okay, so let me maybe go back to that. Yeah, so here, this is kind of funny because this is so, so we're measuring phase jump, all right? And so the only possible values we have are integer values of times 2 pi, right? So you can see we can either go 4, 6, 8, or 10, right? So this is data, but it's very uninteresting in a way because it's just showing 0. Now we can also plot fringe visibility. You can see there's noise in the fringe visibility, but if we count the actual phase jump, that's rock solid. So there's a big stirring, you could say, when we bang it with a laser pulse at this point in time. But after that, it's sitting, which is like a rock solid circulation. So remember, this is a steady state condensate, so the density is not changing in time. So we're whacking it with a hammer, it scrambles, and then it settles down to circulate, and then it stays doing that. How are we seeing the circulation? Okay, so let me go back to these here. So this is our data, okay? And what you see is when it's circulating, there's actually extra fringes. So there's actually 2 extra fringes on the bottom. Yeah, so essentially, this is what we get as data, all right? From this, we can extract the phase winding by analyzing it, and we get this. And so the circulation corresponds to a gradient of the phase winding around that circle, right? And so you can see they're in opposite directions, right? So this is phase going 0 to 2 pi this way, and here it's phase going 0 to 2 pi the other way. So here we can see the handedness. Now, what that means in the raw data is that this one has extra fringes at the top, and this one has extra fringes at the bottom. And somewhere in here, there's a fork where there's a phase defect, all right?
Okay, Maciek, please.
Hi, I will have a question about the last part, which you didn't have enough time to speak about. What's the mechanism in your higher elevated temperatures of condensing into not the ground state, so the lower polarity?
Yeah, so that's a good setup for the slide that I skipped, right? Yeah, so let's see, where was that? Yeah, okay, so one way to think about it is if there was fast conversion between the upper and lower polariton states, you would always just get a condensate in the lower state, right? You could never, because the condensation always seeks out the ground state. But what you have here is a sort of slow conversion, but not zero conversion between the two. So that means to some degree they act like independent populations, all right? And so if you view them as having roughly equal population based on just a Boltzmann occupation, just saying we threw in a bunch of particles, roughly half in the top, half in the bottom, okay? At that point, whichever one has the lighter mass is going to win, right? Because the lighter the mass, the more degenerate and the more likely to become both condensed, all right? So if you look at these curves here, you can see the masses are not equal, right? So this one has a lighter mass than this one does, right? So here, this is inherited, for this particular detuning, it's inherited more of the photon mass, and this one has more of the exciton mass. So this is the lighter state. And so if you simply say, like, I have two equal populations, whichever one has the lighter mass will become a condensate first. Once it does that, the condensate now sucks other particles in. And so now it becomes metastable because it wants to condense, you know, the condensate will now draw other particles into it and prevent the other one from becoming a condensate.
So at this boundary, the masses are comparable of both? The boundary between...
Yeah, so the boundary here is basically just looking at when the degeneracy is equal between the two, all right, at a given temperature, all right? So clearly, like at very low temperature, you're always going to get a lower Plareton condensate, all right? If you go to high temperature, then essentially you just have equal populations of both, and then whichever one has the lighter mass will always be the condensate, all right? But there's this sort of dependency in between where it kind of depends on both temperature and detuning.
Thanks.
Thank you so much.
probably out of time, right?
Unfortunately, we're running out of time, so I will keep my questions for a coffee break.
Okay, great, all right.
But so please, let's move to a next talk. And thank you so much. So the next talk will be given by Seroy Dash about the spin-orbit torque in 2D ferromagnet from the University of Chalmers. Yeah. Yes, please. Floor is yours.
Okay, good morning, everyone. Thank you, Chairman, for the kind introduction. And I thank the organizers for having such a nice conference in a beautiful place. So I am Saroj Das from Chalmers University of Technology from Sweden. And I changed the title a bit because looking at the broad audience here, charge and spin transport in 2D material heterostructures. Of course, I'll be talking about spin orbit torque as well. But I'll start with some charge-based devices within 2D structures. So I come from Gothenburg, and it's a beautiful town. If you come by, just you can send me an email. And we also host European Commission infra-chip project. So if you want to make your device, it's for free for your travel and for your stay and fabrication. And basically, we are a group, Spin and Quantum Technology Laboratory, doing spintronics and quantum electronics. And we have the group, actually, many PhD postdocs and some master students who are contributing to this. So to start with some motivation that, of course, you know charge-based electronics, how the transistors have been scaled down from very big structures to 2 nanometer technology recently, and then there are challenges how to go beyond that, if we can achieve a little bit more or much better than what we have now with silicon technology. So I'll be showing how 2D materials can be useful in this context. And going beyond charge, so spin-based, so you can use spin of electron instead of charge for different applications from quantum computing to brain-inspired computing to quantum spin Hall state and spin logic. So today I'll be just more focusing on the spin logic devices we make out of graphene. And finally, also in a parallel line, something is developing. It's called the spin-based memory. So magnetic random access memory. So they use these magnetic tunnel junctions on top of a MOSFET here. You can switch this magnet with applying a current through these transistors. And this is very nice non-volatile memory, and logic devices can be made out of this. And also how 2D materials can be used here. These are the 3 subjects I'll be covering. So that gives me the opportunity to explore the 2D materials, because you will find all kind of varieties from graphene, semiconductors to magnets and superconductors. So that's the beauty of this. You can explore all the van der Waals materials to make devices out of this. So let me divide my talk into 3 parts. So in the first part, I'll show how we make transistors out of this 2D semiconductor. So it's a semiconductor conference, and we had this recent result on arXiv. So I just wanted to show you that we can make very narrow nano ribbons by top-down approach, by etching on a scalable way. We can make very small narrow ribbons so that the performance actually improves when you make it narrow. So that's contrary to what you expect in other semiconductors. And next, I'll show how we can build a spin logic device. It's a long story under the Graphene Flagship program in the European Commission, and that needs lots of effort to demonstrate. And finally, I'll show you how we can make a spin-based memory device using this 2D material heterostructure, which you cannot do with conventional materials. So first, about the transistor. So you have been seeing that how the transistor is scaling down. So there was a wall here we all talked about. Now they could break this wall coming to 2 nanometer technology. But I see now a second wall is there, whether we can scale down below that or we can improve below that. And there are opportunities to have 2D semiconductors in a vertical geometry as well. But there is a real bottleneck in the silicon technology. So this is the 2 nanometer technology. So from IBM, and you see this is the layer stack they use. So this is silicon layer, and this is the germanium layer around this. The width of these channels are around 40 nanometers. So we talk about 2 nanometer technology, but the width is 40 nanometers. What is the problem? The problem is that if you reduce the width, the current density goes down because of the scattering. So this is how it follows over the years. The channel width, if you go down around 40 nanometer, it's saturated over more than 10 years. And there is no scaling. The channel length, of course, scales down very nicely. So the problem is that you have the depletion around on the surface of the silicon with the electron density or hole density, and also lots of scattering at the edge. And on top of that, in a NMOS and PMOS, you know there is a mobility mismatch. PMOS have lower mobilities, so you need even larger width for PMOS. So how to get rid of this problem? So it was a surprise to us, and there are also other groups working on this in the US. So physically, people could etch down up to this width by reactive ion etching. And we have also done that up to 15 nanometer width. And basically what you expect in a silicon or a conventional transistor, you channel the current density goes down if you scale down the width. But instead, what we observe, it goes up. That can be interesting. So I show you some of the experimental data, and in details can be found in this arXiv paper. So we tested monolayer and bilayer MOS2. As you see, the current, it's a normalized current with width. So 50 nanometer width, 40 nanometer, 30 nanometer. So the current is going up. And even in the bilayer, it's more pronounced. From 80 to 30 nanometer, you can observe such an enhancement. And of course, because it's normalized, it should saturate, ideally. But that also happens below 30 nanometers. So that's a good news that if you plot this for the current density with the width, as you see, these are the literature values. This is for the monolayer in our case, and this is for the bilayer. We scale down to very narrow samples. You see the current density first increases and then saturates. That's actually what is expected, maybe for a better sample. And the mobilities and the threshold voltage also improves as it's going towards 0, as you see here. And the on-off ratio of our transistors are also in a good range. So that is about these transistors. Just a quick update, and if you have more questions, you can ask me. And then I wanted to move to the spin-based device because that was my chairman was expecting I should present more spintronics. So what is spin logic? So we actually could construct a spin majority logic gate, and that's what I will be showing, how we fabricate this device and what are the problems, how we solve this. So spin logic. So there have been several proposals in around 2007, 2010 about how to make spin logic. So they were not looking for graphene. They were having, it's a model they use. It can be any channel material. So it can be copper or aluminum. But the idea is that you have nanomagnets sitting far apart, or it can be close also. Then you communicate this between the nanomagnet by a spin current. And this spin current should switch these nanomagnets. So if you can do that, you can do all the logic operations. So there have been a challenge. So there was no real good material where spin transport can take place in a longer distance. So whatever you have, giant magnetoresistance, tunnel magnetoresistance, the spin transport always happens within a few nanometers. And there have been materials like semiconductors. So I was also doing my PhD in Stuttgart, working on silicon as a spin transport material. I know it's not so easy. So the spin transport length, of course, varies if you dope it or if you have different kinds of spin relaxation mechanisms. So these are the main spin relaxation mechanisms in any semiconductor or any material. Elate effort is the momentum scattering, so spin off can flip if you have a heavy atom, and Economic pearl is about broken symmetry. For example, gallium arsenide is a broken symmetry material. So the spin flip occurs because if you have such a spin relaxation mechanism. And also gallium arsenide and gallium nitride kind of materials can have nuclear spins. So they can also flip the spin. So we were looking for a material, and it was coincidence that graphene arrived into the picture. And you can see it have a nice Dirac cones so that you can have long spin coherence length because the spin or bit coupling is very light. So with the very light elements like carbon is very low. And the spin diffusion length can be more than 10 micrometers, spin lifetime can be nanosecond at room temperature. So that's a perfect platform. And so this is a design made by my PhD student. And now he's working at Intel because he demonstrated a spin logic, and then Intel liked the idea. So this is how we do it. So we have graphene channels. So this is, we make out of CVD graphene, chemical vapor deposited graphene. You can buy commercially, pattern them like this. Then you put ferromagnetic contacts. Ferromagnets, you know, have spin polarity electrons. You inject the spin polarity electrons into graphene. Then over tens of micrometer, you can make any contact or circuit to realize your functionalities. So to start with, so a bit of a history. So most of you know when the spins were first discussed in the context, then giant magnetoresistance, tunnel magnetoresistance got this Nobel Prize. Then lots of research went on to spin transport in metals, semiconductors, and graphene. And then of course, we developed during last 10, 15 years, the scattering mechanisms in the graphene, long coherence length, tunneling of spins. And then in our lab specifically, we were focusing on the CVD graphene, chemical vapor deposited graphene. And we could buy commercially and make the device, and it works at room temperature. So we could show the long distance spin transport, we could make spin logic, we can make spin circuit with multiple branches. So that I will be showing how graphene spin valve devices can be used for memory, logic, and sensing. So what is the graphene spin valve? So this is all room temperature measurement. Of course, you can cool down, the signal goes up, but signal is quite nice if you even at room temperature. So what we do, we take graphene and a wafer and cut down into these narrow ribbons. Then we put the ferromagnetic contacts and the non-magnetic contact like this. So we have one ferromagnet here, and it's a non-magnet. We apply a current, inject spin into graphene. and the spin diffuse. Then we measure by the voltage by a non-local measurement. So most of you know that it measures the chemical potential of the spins. So there's no charge current flowing here, only spin diffuse to the right will be detected. And the spin valve signal the change in the resistance, the voltage divided by the current, is plotted here. You see it crosses around 0. That means its resistance is not 0. It's a chemical potential we are measuring. So when you are up, we are measuring up spin. When you are down, we are measuring down spin. So this is for the parallel and parallel orientation of these two magnets. So they have different coercive fields. They switch at different fields. So that's like few ohms of signal at room temperature. And if you plot the resistance of the signal with the length of the channel, so we could make device with different lengths of the channel, and you see exponentially it decays and depends on the polarization of the contact, resistance, spin diffusion length, and if you plot that, you find the spin diffusion length, which is around few micrometers. So you can make another kind of experiment. It's called spin precision, Hanley spin precision experiments. Maybe you know from semiconductor and physics point of view that when you apply a perpendicular magnetic field, spins will precess around about the field. And that happens without switching the magnet. We keep them parallel, or we can make them anti-parallel. You see the signal behaves like this. So this is the measured signal. And as you see, so this is for parallel, anti-parallel. And if you sum up, the signal adds up here for the parallel, anti-parallel. So if all the criteria is satisfied, you know that you have a spin transport in the channel. And we can fit this using spin diffusion, precision, and dephasing. So we don't have spin drift because we don't apply electric field between the channel. So diffusion constant, the precision Larmor frequency, and spin dephasing time, we find the spin lifetime around few nanoseconds. Of course, so I showed you the signal is few ohms. How to improve the magnitude of the signal? So we were using a aluminum oxide or a titanium oxide or a magnesium oxide tunnel barrier, which is have pinholes, defects. So if we use a 2D tunnel barrier like boron nitride shown here, what we see, the signal is much, much higher, and the spin polarization we calculate from this signal is going up with a number of boron nitrides. Up to 3 layers of boron nitride, we see spin polarization goes up to 60%. And for the few layers, monolayer, bilayer, it's a bit smaller, and because it can have pinholes also. So that's good. So we can inject efficiently spins into graphene at room temperature and transport over several distance. And this is the part of the graphene flagship activities. We scaled up the CVD graphene devices over 4-inch wafer, make devices of multiple channels, different circuits, and finally, how to realize such a spin logic device. So I'll be showing now the majority logic. So this is the basic idea. So if in this room I want to take a vote that at least we need 3 people to have a majority, no? So with 2 people, if I say yes and no, then we are in a tie. So we cannot actually come to a conclusion. So to realize something, you need at least 3 votes. So A, B, C are the 3 inputs. And then these are the graphene channels. As you see, these are 3 ferromagnets giving the inputs, and 0 and 1 can be defined by the spin, whether up or down. So how to do that? So if we apply a negative bias, so we inject spin into graphene, you accumulate, let's say, down spin in graphene. So if you change the bias current to positive, you extract spins from graphene into ferromagnet, because ferromagnet will accept only majority spins. So in that case, you accumulate more red spins in the graphene. So the spin accumulation in graphene can change from up to down just by changing the bias voltage from plus to minus. That's very simple. So you have accumulation of up and down spins in the graphene channel. So if you say 0 is down and 1 is up, so you can have all the combinations for A, B, C, 3 inputs. And you see that the truth table should look like this. So when 2 inputs are 0, output is 0. When 2 inputs are 1, output is 1. So it's a majority logic. So how the signal look like? So as you see, we have 3 inputs, A, B, C. We apply current of different magnitude because this A, B, C are not exactly the same, not sending the exactly same amount of spin because they have different polarization a little bit. So the current levels are also a bit different, but you can optimize your device to have better currents, the same currents for the ABC. Then the output signal, what we see here, and it's a non-local measurement again, the voltage signal as you see, and if you put a comparator here, you can realize all these logic operations. Okay, so then if you switch the output signal, reverse the magnetization, and then you can also do all the reverse operations. So basically, for this set of data, you can have AND, or NAND, and NOR. So all logic, so it's a majority logic, and you can make it a universal multifunctional logic. And it's very stable over time, and you can see for the parallel, anti-parallel, it also changed the sign. So that's very good. So, but I don't know whether it will be applied or not, but it's just a basic demonstration, I would say. And then, as you know, graphene is a beautiful material for many purposes. Not only because it's a monolayer, it have high mobility, but because it's also that you can tune the properties by proximity. So because it's a single layer, you put something on top, you change the properties. So if you want to induce spin orbit coupling, so you can also put a high heavy metal or a 2D semiconductor which is having spin orbit, you can induce spin orbit coupling in graphene. If you want to make a graphene a magnet, so you put another magnet close to that, it will proximatize and get the magnetic properties. So that's what I will be showing. So first 2 examples. How to induce spin orbit proximity in graphene. So for example, graphene have a nice Dirac charge neutrality point, then you can open a gap, and it's a spin orbit gap. You can open, if you put, for example, a 2D semiconductor on top. So this is our graphene device. We put a 2D semiconductor. I'll show you how we can induce spin orbit coupling. And also, if you put a magnet on top, you can also create this splitting in the bands due to, it looks like a Zeeman splitting, and that you can also realize. So if you have also both spin orbit and Zeeman splitting, it will be a bit more complex. So that's what we are working towards now, but I will not show those results. So I'll basically show how spin orbit behaves. So there have been lots of research already in this line. So we were kind of first to predict or show that when we have a graphene channel, we put a 2D semiconductor on top, we send spin current. Again, we are doing with all the spin, because spins are very sensitive to spin orbit coupling. So spin goes in the graphene channel, and they experience the spin orbit coupling. So what we see, the spin valve signal, you see very small in magnitude. Instead of ohms, it's in milliohms. And the handless spin precision, instead of nanoseconds, we have picosecond, tens of picosecond lifetime. So we reduce the spin signal and reduce the spin lifetime when we put something on top of the graphene. And when we apply a gate voltage, what we see, the first reduction happens in the magnitude and the lifetime because of the spin orbit coupling. And when we see it's a N-type semiconductor, when we go to positive voltage, so some spins are getting absorbed by MOS2, and then we lose the signal. But it shows that we could induce a spin orbit coupling around 1 millielectron volt in graphene. Of course, you can choose different materials. So here is another example that if you put a topological insulator on top of the graphene, it's a bit complex device. We have a hall bar device of graphene, and we have a ferromagnet for injecting spins into the channel, and we detect a voltage here across this hall bar when we have a graphene topological insulator heterostructure. So what you expect that you have a graphene band, a TI band. If you combine that, in the graphene band should have a spin orbit texture. And the spin texture is calculated by Stefan Ross group. This is in this paper, that outside the charge neutrality point, spins are more in plane. And if you go close to the Dirac point, it's more out of plane. So the spin textures can be also tuned in the graphene bands. So what we have done in the experiment that we could inject spins, detect a voltage here. Depending on the magnetization of this, we can switch the signal. That means we are measuring spin transport, spins coming to these heterostructures. And then we could measure the Hanley spin precession signal also, and this changes sign when we change the gate voltage. That means we are probing either in the conduction band or the valence band of the semiconductor. So and we could calculate that we have a spin orbit coupling in the graphene. Then about creating magnetic exchange interactions in graphene, we have to go to look for not only ferromagnets, which is conventional, but some 2D magnets. Yesterday you have seen a nice talk by Marco about this 2D ferromagnets. So there are a number of ferromagnets based on the compounds you have and the Néel temperature, or the Curie temperature, more here. So this is room temperature. We are focusing more on the room temperature metallic ferromagnets, but for proximity effect, we could not find anything room temperature rate. So we use chromium germanium telluride, which is a bit low temperature. So this is a review article. You can have a look. So we try to cover most of the advances happening due to 2D magnet and what kind of devices by spin valve, TMR, and spin orbit torque devices we can make. So coming to the magnetic proximity effect, so we do similar experiments. As I told you, spins are sensitive to spin orbit coupling. Also, they are sensitive to any kind of proximity effect due to magnetism. So similar device, so we put a graphene channel here, we put a ferromagnet, we inject spins, and the spins propagate under the contact, under the material here. This is a semiconductor, so there will be no spins going into this material. If it's not conducting, then we measure the voltage. And this is the Hanley spin precession signal, the resistance change with magnetic field, out of plane magnetic field. At room temperature, you see there's a blue and the red curve, up and down sweep with magnetic field. So they are on top of each other, so very good. But the Curie temperature of this magnet is around 70 Kelvin. So let's see what happens when you cool down. To 50 Kelvin, we see a splitting. That we could simulate with the magnetization of this material, and we should be able to see that we proximatize graphene with this magnet, and we create a spin or magnetic proximity or magnetic graphene. So that also we can track with temperature, as you see here, from 40 Kelvin. Because when you cool down more, we see some weird effects coming from graphene, actually. This is due to weak localization, weak anti-localization kind of behavior. But above, around this temperature, we see this splitting. And this splitting survives even beyond the TC of the magnet. So proximity effects can be also, around the interface, things can be a bit different. So we see that this beyond 70 Kelvin, we see this splitting still. And this is how the temperature-dependent signal looks like. So you can make your graphene spin orbit and magnetic as you wish on demand. So you can put at some places whatever you need. So the next challenge is how to create spin orbit plus magnetism both together. We are working on all heterostructures, putting 2D magnet on top and 2D spin orbit material from down in the graphene. So that's an ongoing project. I will not be showing anything there. So the last part about the graphene thing, I wanted to show you how this can be used for sensing spin in graphene for many kind of materials. So it's like a test experimental equipment for us. So we have to make a device, of course, but we can test any kind of material. For example, if you put a 2D magnet, you want to know what is the magnetization, what is the spin polarization, you can do that. If you take a topological insulator, you apply a current and you create this spin momentum locking, that spin will be injected into graphene. You can know the spin polarization of this topological insulator. We can do spin pumping experiment. You can do 2D semiconductor with a laser. You pump the valley polarization into graphene. You can also detect with a ferromagnet wild semimetals in the same as topological insulator. and also you can create the domain walls or spin patterns that you can do detect a spin texture in graphene. So it's a very versatile platform we are trying to develop. So the first I will show you how we inject spin into a ferromagnet, from a ferromagnet. So that's what you see. We have a device, we have a graphene channel, we have a 2D ferromagnet. It's around 20 to 30 nanometers. It's not really monolayer. So it's an iron germanium telluride. And at a room temperature, you can see nice spin valve signal. The first switch you see due to this FGT, and the second switch is due to cobalt. So we have one FGT and one cobalt. Why we have like this? Because we know the properties of this cobalt very well. In a multiple device, we have different cobalt contacts. We can characterize what is the polarization, and we know it's in plane. Then we can find out what is the polarization and the magnetism in this. So nice experiment is this Hanley spin precision experiment. So what we want to know, what is the spin polarization orientation? So whether it's in plane or out of plane or canted. So for example, this is field is x direction, so this is x. So if your magnetization is in plane and x direction, you should not see any Hanley precision because spins and the magnetic field are in the same direction. So if you have a perpendicular direction like this, magnetization and the field, you should see such a symmetric signal. But if it's perpendicular, this is the field, this is the magnetization, you should see asymmetric signal. What we see is we measure for both magnetization orientations, we average out. This is asymmetric signal, and that means we have a perpendicular magnetic orientation. So it's a very soft magnet. We can change the magnetization very fast. Then if we do a G direction, so the magnetic field is now like this, we also see both symmetric and asymmetric components. So what does it mean? So it has spin polarization in all directions. So that means it's a canted magnet. So that type of behavior we can probe. Also, we could see that the spin polarization, if we compare to cobalt, so these are two cobalt contacts, and this is one cobalt, one FGT, the magnitude are opposite. The signal sign is opposite. That means the spin polarization is negative for FGT compared to cobalt. And the DFT calculation also shows that the spin polarization at graphene and ferromagnet interface can be up to 45%. And we can also measure spin textures. So by accident, when we are making this flex, we get a kink-like feature here in the flex. This kink-like feature pin the some domains the spin textures. So these materials have also high spin orbit coupling. So you can have a spin texture in this material naturally. And what we should expect in a conventional device, it's more like this. If you have spin textures, you start switching your magnet and it will behave a bit more complex because you have a complex magnetic texture. So that's what we also observe in our experiment. Now spin valve signals, as you see, it's blue lines going up. Now it switches before zero, and that you can explain by a spin texture spin valve. And as I told you, we can also use this graphene spin valves to detect spin polarization of any material which you think can have spin polarization by applying a current. For example, it's a topological insulator, so we could see a nice spin valve signal and a Hanley spin precision. Here you see one switch because you have only one cobalt to switch. The other is not a ferromagnet. Other is just a conventional topological insulator. It's not a magnet, but it can generate spin due to spin momentum locking. So you take a cross here, you apply a current, then you can see what is the spin polarization coming here. And that is very useful technique, even you can do at room temperatures. And this is a similar experiment. I just wanted to show that tungsten telluride, it's a material like a wild semi-metal, but it have also broken symmetries. And we also see unconventional spin polarization. Basically, what you should expect, the spin current, and the charge current should be orthogonal to each other. But here, what we see, they are also breaking the symmetry rules because that is, it's a broken symmetry material. So with this, I would like to come to the third part of my talk. We have 7 minutes. I see that how we can build a spin memory device. So how we came to this, because this is a tungsten telluride, which actually allowed us to think a bit differently what people use in the conventional spin or bit torque materials. So what we need actually is spin current, which can be out of the plane to the geometry. So let's come to that. So you have a material where so conventional materials like platinum should give the in-plane spins when you apply a charge current due to spin Hall effect. And in a broken symmetry material, spins can be other directions as well. And if you have an out-of-plane spin, so that can switch an out-of-plane magnet much easily than the conventional in-plane spins. So that's a main challenge. So let me introduce to the field. So in 2011 and 12, people have shown that you can make a spin or bit torque-based device. So they use platinum or heavy metals like this. You apply a charge current. You create spin polarization due to spin Hall effect. So because the spin can also exert a torque in this magnet, and that magnet can switch. If you switch this magnet, then you can read out this magnetic by magnetic tunnel junction as a resistance change. That's what you see. So there is no magnetic field here just by current. You switch this magnet. They actually use an assisted magnetic field for some broken symmetry regions. I will come back to that. But within 10 years, less than 10 years, so IMEC in Belgium, they showed that it can be a scalable technology. And in 2023, TSMC announced that they will be producing memory out of spin or bit torque. So it will be competing with spin transfer torque, which is already in the market. So you see many automobile companies and many gaming companies or space companies, they are using magnetic random access memory because it's non-volatile, much faster, and have higher endurance. But this can beat those performance as well, but there are challenges. So first of all, when you use this material, spin polarization you create is around 10%. Maybe you need higher efficient so that you can use less current to induce a larger spin polarization. And the spins you create are more in plane, and industry wants out of plane magnets because you have your magnetic data storage, which is perpendicular because you want to have more capacity for your magnetic storage. So industry wants out of plane magnets, so then this cannot work. So you need to generate out of plane spin to switch a out of plane magnet. So very nice, then we come to the basic physics. So we can have lots of basic physics phenomena. Spin orbit, magnon, topology, symmetries can be playing a big role, quantum geometry and chirality. So if you consider those things, you use these materials, you generate larger spin polarization and can be out of plane. And on top of that, you can also use 2D materials, then proximity, twistronics, strain, and all the electrical probes, as you see here, can be used to manipulate and play. So with that, we have this European project. I am coordinating the Pathfinder under Graphene flagship. So what we use such a material with a broken symmetry, like tungsten telluride, tantalum iridium telluride. Then we plan to use 2D magnets. So then, thing is that, so first we take this material, tantalum iridium telluride, which is similar to tungsten telluride. So it's a broken symmetry along one plane. So you make first conventional device with a nickel iron, which is a ferromagnet, but you make a spin or bit torque ferromagnetic resonance experiment. As you see here, you see the voltage signal with magnetic field when you have a resonance. Then you have a symmetric, asymmetric component. So because it's a lower crystal symmetry, we are generating also out of plane spin. Conventional material, when they have symmetric, then it's more in plane spins. So that's the difference. And we want to see, so this is the voltage signal at different angles. And I plot now symmetric and asymmetric components with angle. and we fit with these equations having different torques. So what torque we generate or exert from on the magnet. So if you see in the x, y, and z direction, we have different torque magnitudes. So this is in percentage, for example, this is 11%, this is 8%, this is 4%. So in the z direction, out of plane, it's the maximum. So that can help to switch a perpendicular magnet. Also look at this number. So this number is 4 times 10 to the power 4. So this is called out of plane spin Hall conductivity. We estimate when we put a tantalum iridium telluride and put nickel iron on top. Nickel iron is not a 2D magnet. So now let's see what 2D magnet can do. So this is a out of plane iron gallium telluride. TC is around 370 Kelvin. Nice anomalous Hall effect you see at room temperature. So it's a perfect candidate. So now we make heterostructures of tantalum iridium telluride with iron gallium telluride. So you see nice anomalous Hall effect when we sweep the field. Now we switch up the field, even doing the sample outside the magnet. It's actually a Helmholtz coil we use. Then what we see here, that by current we switch these magnets at room temperature without field. So that satisfies all the criteria that you can switch a magnet without applying a field at room temperature with a very low current density. And we could estimate the spin orbit torque parameters. For example, how we do that is a Hall measurement. So we apply a current and measure the resistance voltage here, the second harmonic voltage. So when it's a nonlinear effect, like we exert a torque and magnet oscillate, and we can measure the second harmonic voltage, how it changes with angle. So that's from this different magnetic field, we can estimate the torque component. So it's a damping like torque, what you say. And also you can do similar experiment if you do second harmonic signal with magnetic field sweep. So the magnet diverges, it's an in-plane magnetic field. So as you see, we diverge, we fit this with the similar equation I showed, then we can also find the damping like torques components. And then now interesting thing that I want to now compare the spin Hall conductivity. So what I have shown you before in this tantalum iridium telluride with other conventional magnet, it's more here, 10 to the power 4. But if you make a clean interface with all van der Waals, so the numbers are here. So this is with a tungsten telluride, iron germanium telluride with a low temperature. We have room temperature because iron gallium telluride, another magnet, the magnitude is much power density we use is much smaller and much higher spin Hall conductivity. And this is a very nice example what can be done with new kind of material. But I just told you that it's an exfoliated flex from a single crystal. So we still need to grow in a scalable way to show that it is really behaving in the same way. So far from applications, but nice physics. So I have few minutes left, so I can show you maybe some recent results on the alter magnet. So we have a new Pathfinder project on alter magnet, and we want to switch the magnetic needle vector or use it as a spin source. So Marco gave a nice introduction to alter magnets. I don't go through. It's a ferromagnet, antiferromagnet. You break symmetries here to get an altermagnetic band splitting. And the splitting can be much, much higher. I focus on this manganese telluride here. And we grow this material in collaboration with Greece from Thanasis Stimulus. And it's a manganese telluride phase, as you see, very nice crystalline structure. We see in the nil temperature, below room temperature, magnetoresistance curves like here, and also anomalous Hall effect. Perfect. So that's what we will do now. We grow chromium telluride, a 2D magnetic material on top of that by molecular beam epitaxy. So it's a bit thick now. We are trying to scale down to a few nanometers. And we make a Hall bar device. You see nice anomalous Hall effects coming mostly from chromium telluride. So as you see, it's working, but at a low temperature because we wanted to check the manganese telluride properties. So we measure at 150 Kelvin where manganese telluride is a alter magnet. And by applying current, we switch. We switch the chromium telluride. So as you see here, that's very stable over time. But as you see here, I was trying to explain you the symmetry principles. It gives an in-plane spin, so at zero field, you don't switch. In tantalum, iridium telluride, tungsten telluride, you could switch at zero field. But when you apply field, you break the symmetry, so then you switch. So that's a basic difference, but these devices can be useful to investigate the magnetic properties, or the altered magnetic properties of this material. This is just the beginning. So I would like to summarize that. I could show you a few examples how 2D materials can be useful, which we cannot use, where we cannot use conventional materials. And I would like to thank you for your attention and also the funding agencies.
Thank you so much. Yes, please.
Hi, really nice talk. I have a question regarding the first part of your presentation. So usually, as you mentioned, like by narrowing the channel width, your ID actually drops.
Yeah.
In your case, it's opposite. Could you please explain why?
That's we don't know, but we expect that we don't have a depletion region. So as you know, in the conventional semiconductors, so on the surface, let me go back. So in the conventional semiconductor, we should have a depletion region. So for example, I think we have no depletion at the edge. And there are evidence from STM experiments that on a 2D semiconductor, the edge can have a higher current density or the charge density, and some current, more carriers are at the edge. So that may be one region.
Okay. And just another quick, I have curiosity. Have you tried changing the TMDC, different type of TMDC, just to see which, for example, is it valid for all types of TMDCs, or particularly MO based or W based?
We are trying to do that, but I know other groups in the US at Stanford, Purdue, they have similar results. They also see very similar behavior, but they have only measured up to 30, and we could go down to 15. But people have now reproducing on different TMDs. But you have to use a gentle etching procedure, and you can find their details here. If you use normal argon ion, it makes a damage.
Okay, thank you.
Very interesting talk. I have two coupled questions. So the first question you briefly mentioned in the very end, but can you comment in more detail how much the interface affect the performance of all these spin devices? And the second question is how, if it is strongly affected, how much does it influence the reproducibility of these devices if you make, I don't know, 10 of them? What would be the yield rate?
Yeah, very nice
Thanks.
question. So as maybe Kai was presenting in the first day, that these are handmade devices. And of course, what we see, there are lots of variations from device to device. Yield is around maybe, for the graphene device, it's a different story. It's scalable. It works most of the time. But for the spin orbit or device, I think you mean when you stack them on top of each other, yield is 10%. And then the efficiency, most of the devices, for example, tantalum iridium telluride, we measured, successfully measured 5 devices out of maybe 50. So, but the efficiency was very similar on all the devices, because we stack them in a glove box. So we kind of protect the interface. But if you do in the air, things will change much more. But there's a main problem, and now we are in collaboration with many groups and doing MB growth. We also grow this type of materials, trying to put them together in the project. Yeah. So that's the future, to grow materials. So I know in Poland there are Janusz in Warsaw, they have nice MB machines, so we can, yes. So we can collaborate and try to make scalable samples.
Thank you very much for, I'm here.
Yeah.
Thank you very much for this nice talk. My question is regarding the integration of the FGT with the TMDs, and that is especially about the lattice mismatch. And the next question is regarding the conductivity of the FGT, that is the iron gallium telluride. Will it affect the spin orbit coupling in special disk devices?
Very nice question. So first of all, about lattice mismatch. So if it's a van der Waal epitaxy, I think MBE people can better answer. Maybe they don't need that lattice matching. I am not an expert in MBE growth. But the second question about the conductivity and the TMDs, when you say 2D semiconductor, when you put FGT on top, 2D semiconductor, then most of the current goes through the FGT because it's metallic. And the torque, what people have seen, we have not done those experiments mostly at the interface. But here we choose tantalum, iridium telluride, tungsten telluride. These are 1T phase, which is metallic or semi-metals. So the conductivity are much higher. So we can see spin orbit torque coming from the TMDs.
Thank you.
Thank you. Concerning manganese telluride, usually here.
Yeah.
Concerning manganese telluride.
So nice to see you. When I was a PhD student, I used to attend a conference you organize, Spin Tech.
Yeah, thanks. Couple years ago.
Yeah.
Concerning manganese telluride, as we know, there is a lot of domains typically in this material. And did you take care about that, or?
Manganese telluride is so very nice question. So that there are magnetic domains. We are trying to. So this is the first experiment I just wanted to show because some people are interested to grow here. So we are making different devices with very small devices below micrometer to see how this is affected. So for now, we don't have knowledge about domains, but we are having beam time in September or October to measure by XMCD PIM.
And do you know what was the sign of anomalous Hall effect? Because there is controversy about sign of anomalous Hall effect in manganese telluride.
Sign whether up or down.
Is it Hall-like or electron-like sign of this anomalous Hall effect?
No, I missed. Maybe you can update me. Yeah.
Okay.
Thank you.
Thank you.
Very, very short one, Bruno.
I promise. Thank you. My
short.
question is more or less what Arka asked, but it's about these nanoribbons of tungsten molybdenum sulfide. Sorry. Did you see, or are there studies about the influence of the type of the edge over these properties that you're seeing?
Yeah. So we have not done such characterization. I see lots of optics group here doing photoluminescence. I think that will be nice to see what are the properties of those edges. We have not characterized yet those properties.
Okay. Thank you so much. Thank you for a nice talk.
Thank you.
Yeah, and please make note, this is the short announcement from the organizer. Please wear your conference t-shirt during the photo. This is a small request from them. Thank you.
wyglądające, tylko prosiłbym, żebyś siedział gdzieś tak bliżej.
Yes, Joe. Yes.
Dear young scientists, dear experienced scientists, now it's a time to continue our work. So please take your seats. Since we need to be in time for a photo, I would like to invite you to the conference. And in this session, we have 5 speeches invited and 4 contributed. I'm Renata Butkutė from the Center for Physical Sciences and Technology, Lithuania. And the first lecturer will be done by Philippe about defects and positrons in ultra-wide bandgap semiconductors. So the floor is yours.
Okay, thank you. Thank you, Renata. Nice to see all of you here. Before I start my talk, I'd maybe like to express my thanks to the organizers, as is customary, and special thanks, of course, go to Anja Kafar and Anja Raska, who have done such a great job in making everything happen together with their teams. I'll try to tell you something about defects and positrons in ultra-wide bandgap semiconductors. But before that, I have a few other kind of things I'd like to share with you. First, well, I know many of you, which means that probably the same people know me. But maybe not all of you know the lab where I'm from. So I'll start with that. So I'm from University of Helsinki and a lab called Helsinki Accelerator Laboratory. Is it working? Almost. Yes. Now, anyway, we have some of you have visited us. We have a fairly big infrastructure. The main accelerator is 12 meters tall and it's vertically positioned, so our labs are underground. So accelerator lab means we have a 5 megavolt tandem accelerator, we have a 500 kilovolt ion implanter. We're soon getting a small electron linear accelerator as well to produce positrons. We have a few magnetron sputtering setups. Of course, with the accelerators, we can do all possible ion beam analysis that you can imagine. And then, of course, my personal favorite, the positron stuff. So we have a couple of positron beams and fast positron spectrometers. I'll tell maybe a few more words about that later on. The lab is fairly big in terms of infrastructure. We are fairly big also in the number of people when it comes to a university lab. So there's we are about 20 people of senior personnel. The ones in bold are the ones who have something to do with positron research and somehow related to this talk as well. Plus, we have 50 younger people hanging around, or well, working mostly. So 10 postdocs, 30 and something PhD students, and some master students as well. Okay. Again, the ones in bold have something to do with this talk and positron annihilation spectroscopy. Okay. Short introduction, then let's move on to other things. So I'll start with a little bit of a historical background, kind of making an excuse of why many of you have seen me so many times around Warsaw, for instance. But we have to start a little bit earlier. So this Finnish-Polish cooperation in semiconductor science started already 30 years ago. My name is not here because, well, I wasn't involved yet. But you see some promising rising stars of Polish science here, like Andrzej Wysmołek and Isaac Grzegory, who I think are somewhere in the audience, who participated in this work. So it started with gallium nitride, high-pressure ground crystals, and studying them with positrons and finding that, okay, there's, surprise, surprise, there are vacancy defects in these crystals. So that's how the cooperation started. Then 5 years after, a few more papers, and 5 years later, my supervisors, so Kimmo Saarinen and Pekka Hautajärvi, they suggested, I was doing my master's at Helsinki University of Technology, and they suggested to me that, hey, why don't you do something about this cooperation and go to Poland for a few months? And this is how I became a hang-around member of Unipress. I spent 3 months in the summer of 2002. I worked with some young scientists like Grześ Teser and Darek Wasik and some other people from different institutes across Warsaw. Sokołowska used to look like this for the younger members of Unipress. Then, also, this is not my first time to Jaszowiec. I participated in the Jaszowiec conference twice before, in 2002, 2003. It was called the School on the Physics of Semiconducting Compounds at the time. I think the name changed in 2008 or 9 or something like this, and it was still held in Jaszowiec, by the way. And in spite of it being called the School on Semiconducting Compounds, I was allowed to present a poster on silicon, which was kind of nice. Anyway, this is what the hotel looked like, a little bit different. This is the time of paper photos for the younger generation here. Also, the past, what we used to do there was pretty much the same as here. So, this is, by the way, Christian Rüster. He was doing his PhD at University of Würzburg. I think he was collaborating with Professor Sawicki from IFPAN at the time. It's funny that he's gotten this old, and I still look the same. Anyway, with all this, of course, important activities at conferences, playing billiards and beer. So in the true spirit of Jaszowiec, I ended up getting married to this girl who was presenting a poster next to mine. No pressure on you guys, but and then all sorts of other collaborations started. So before this time, we were working together or our group was working together with the Institute of High Pressure Physics, or it was called back then, I think, Center for High Pressure Physics or something. I mean, it is not an institute at the time. So anyway, I met Janusz Sadowski, who is somewhere here, I guess. Yes, and we started working on. It was fashionable at the time, gallium manganese arsenide. Then, of course, many things followed. So further papers with Unipress, with IFPAN, also with other groups in IFPAN, Grashan, Michelski, Unipress, IFPAN, again IFPAN, another group from IFPAN, Dobrowolski and Łukasz Kilajski. And then Amono came to the picture. You might have heard of the company, who no longer exists as such, but as part of Unipress. Then also Warsaw University of Technology, working on some solar cell materials. IFPAN again, I guess IFPAN, a lot of IFPAN and Unipress, by the way. Yes, weird materials, bismuth telluride. Weird for me, maybe not for all of you. What is there? Yes, and also Wrocław University of Technology. So I met Robert, I think, Kudrawiec also in 2002 at the Jaszowiec meeting when I was here. Good, and then this continues on further works with Unipress. Lots of stuff. I think I calculated something like between our group. So if I count my papers plus those before me, I think we're somewhere about at 40 papers together with different Polish groups working on defects in semiconductors. And then in the first paper, there was also an institute that in English used to be called SINS. This has nothing to do with Jaszowiec now, but it was sort of Southern Institute of Nuclear Sciences, which then was, I think, transformed with some other institutes into the National Center for Nuclear Research. So then it's actually, again, working with them, but not in semiconductors. Anyway, that's for the... I'm sorry, I tried to dig up some compromising photographs from the old conferences, but I couldn't. Maybe it's better that way. Anyway, defects and positrons. So I'm done with the first third of my talk. This is good. Yeah. Defects, and when I say defects, I mean point defects. And of course, you guys are semiconductor physicists, so you probably most of the time think about defects in this way. So you have defects that create levels in the gap. They can be shallow or deep. I'm a simple person, so I like to think of defects in the atomic way. So what they actually, not what they do, but what they sort of are physically, or almost like if you touch them. And in particular, I like to speak about vacancy defects for a reason that will soon be evident. Anyway, the thing is that, of course, with semiconductors, well, I'm not trying to lecture you about semiconductor physics or semiconductors, but of course, you like to introduce dopants. And then what happens is that very typically then you end up having missing atoms as well because of putting in their dopants. And this is because of how thermodynamics tends to work, that it is easy to form vacancy defects that compensate for the conductivity that you're trying to make. So, and these vacancies can be formed either next to the right next to the dopants or somewhere further away. So this is what I'm insanely interested in, these vacancy defects. Then something that I suppose you're less familiar with, my favorite technique, which is positron annihilation spectroscopy. So it's based on a funny particle called the positron. So there is the antiparticle of the electron, same mass, opposite charge. It's also a spin half particle, by the way. How we get them? Well, you can create them either by pre-production, so photons with high enough energy spontaneously split into a positron and electron. You can enhance this splitting by shooting these photons next to some heavy nuclei. For this, you need a nuclear reactor or a free electron laser. However, now we are actually getting an electron LINAC. There's some technological developments that allow to do it in a fairly cheap way. This costs like a couple of million. These two things are a little bit more expensive. Or you can, if you're being cheap, you can just go and buy some sodium-22 in a pharmacy, a little bit special pharmacy. And then you'll get positrons coming through beta decay. So beta plus decay channel is such that sodium-22, for example, decays into a positron and into a high energy photon. And this positron then will, eventually, what happens is that it annihilates with an electron, and you get about 511 keV photons out of it. So these are called annihilation photons or gamma photons for short, even if they're not strictly speaking gamma rays. So that's what you do. We take positrons, we shoot them into a material, they annihilate with electrons, and then we study these and maybe these. Why? Well, positrons, when you inject a positron into a crystalline solid, and after it thermalizes, it really wants to go where there aren't any atoms. So it will first of all delocalize itself in the interstitial space between the atoms, if you think of things in the real space. And in particular, if you remove an atom, this will look like a huge potential well from the positron perspective, that it would like to localize itself there. And this is all because it wants to be as far away from the atoms as possible. Because the atoms, well, at the center of the atom, you have a huge chunk of positive charge. So the positron just doesn't want to be there. So it's very sensitive to vacancy defects because it really likes to go in there. And also it's quite practical because positrons are pretty insensitive to almost anything else in a crystal. And which means that you have a selectively sensitive probe for vacancy defects, and you can identify vacancies, you can tell their concentrations, give in a certain range, which is about from 10 to 15th to about 10 to 19th, which is a happy accident that it actually is the technologically quite important range of defect concentrations. You can study bulk crystals, thin films. You don't have to care about the conductivity from the experimental perspective. They are also sensitive to charge. So while positively charged defects are invisible to positrons because of the, if you want a simple explanation, the Coulomb repulsion, neutral vacancy defects and negatively charged vacancy defects you can identify, and you can actually separate them. So you can tell which are neutral, which are negatively charged that you're looking at. And since and this is by actually the temperature dependence, and of course, since in semiconductors you can manipulate the charge state of a defect by illuminating or by doing some other tricks, you can actually figure out also things about defect levels in the gap. Okay, brief intro to positron experiments. Basic idea, you shoot the positrons into a sample, they stop, thermalize. This takes a very short time, a couple of picoseconds. And then it eventually finds an electron with which it annihilates, and it emits 2 photons kind of in opposite directions. There's here. You can measure 3 things in a simple way, or relatively simple way, or at least conceptually simple way. One thing you can measure is the time difference between an annihilation photon and the photon that is emitted together with the positron in the source. Kind of simple. You measure time differences, measure a bunch of them, and you have some data. You can measure the exact energy of this 511 keV photons. They are not every photon is exactly 511 keV. There's a broadening coming from the distribution of the electron momenta, or momenta of the electrons that participate in the annihilation process. The same momentum of the electrons also causes a little bit of deviation from this 180-degree angle. So you can measure the angular deviation. It's an angular correlation experiment. Nice thing about this lifetime and the momentum distribution is that you can actually calculate them from first principles and compare with experiments, which is kind of cool. So what the data might look like. Here's a Doppler broadening measurement. So you measured the 511 keV electrons. This is photons. This is 511 keV here at 0, so at the center of the peak. There's a folded peak now because it's symmetrical, so you get better data by folding it. This would correspond here to about 518 keV. So there's now I've just put it in electron momentum in atomic units. So this is what the spectrum looks like. Doesn't look like a lot of detail in it, but if you look at it a little bit more closely, almost working. Am I too far from it? Yay, now it works. It consists of 2 parts. There's a parabola, which is a Gaussian, of course, this is semi-log plot. And there's a part that is, well, something wider than a parabola. And this is essentially coming from loosely bound electrons or unbound electrons. A Gaussian momentum distribution means free particles. And core electrons contribute then to this something that is clearly non-Gaussian and sub-exponential even. So we have 2 kinds of electrons participating in the annihilation process. Of course, it still doesn't have a lot of detail in it. But if you point by point normalize the white data points by the black data points, so there is now an experiment where all the positrons annihilate at gallium vacancies, and then the black is when positrons don't see any vacancies in gallium nitride. If you divide them point by point, you get the red points, which now seems to have a little bit more features. You can see that it's above 1 here, there's a shoulder-like feature here, there's a part that is below 1, and the black curve is now the theoretical calculation of the exact same situations. You can compare them in the same plot, which is kind of nice. Very typically, you don't have the time to, these are kind of long experiments to do it like this. So you make faster experiments, you collect less data, and then if like color choices of the figure would be better, you would see that there's a shaded region here. So you integrate this part, you determine the fraction of the counts that is in this part, you determine the fraction of the counts that is in this part of the peak, and you call them the S and W parameters. Maybe you've seen some papers with S and W parameters from positron stuff. This is what they mean. They just tell you the fraction of counts here, fraction of counts here, that describe the shape of the peak without going into the details of what the peak looks like. Otherwise, they mean nothing. They just are shape parameters of the peak. There's no really physical interpretation behind. Of course, core electrons contribute more to the W parameter and valence electrons more to the S parameter, but it's not exactly that. Lifetime data looks like this. There's like a standard decay stuff. You measure a lot of time differences and you end up having something that looks like an exponential or a sum of several exponential components. This is what you get. You can analyze it, you can fit one exponential component or a few of them. The components are in the range of hundreds of picoseconds to nanoseconds. The longer the components, the larger the vacancy defect. A short version of the story. This is a nice experiment because you can separate the component itself and its intensity in the spectrum, and that actually tells you directly something about the concentration of the vacancies. The Doppler-Broglie experiment, this is primarily sizes and concentrations of vacancy defects that you get with lifetime. The Doppler-Broglie experiment is sensitive also to the identities of the atoms surrounding the vacancies, because the core electrons that contribute to this high momentum part, they are of course different for different kind of atoms. So you get differences and changes in the W parameter and of course then in the whole spectrum. Usually also these S and W parameters are shown in something we call an SW plot, where you would have the point describing annihilations in a gallium nitride. This is now an example of gallium nitride where you don't see any defects with positrons. You would get a data point, and then for various kinds of defects you have a specific point in this SW plane, and then data points measured in samples. If they contain, for example, a certain kind of defect, the data points, depending on the concentration of the particular defect in the samples, will fall on a line connecting this point and the vacancy point. And by that, you know which vacancies you're looking at, and what is their concentrations. Short version of the story again. If you're particularly interested in this technique, there's a review that we wrote already a fairly long time ago. It's 50 pages on positron annihilation, so it is also very helpful if you have trouble falling asleep at night. So then let's move to the semiconductor part. I promised to say something about ultra-wide bandgap nitrides and oxides, and the reason why many people are studying them, including us, is power electronics. This is the classical thing you show, and you're looking at seeing that when you increase the bandgap, you get better and better performance, or potentially you get better and better performance from the power electronics perspective. So if gallium nitride is here, then you can think of looking at beta gallium oxide or looking at is alloys with aluminum oxide or aluminum nitride and argon alloys. And of course, the classical question is then that, well, in order for a semiconductor to be useful, you like to dope it. Best if you could both N-type and P-type, and of course make it insulating. And it is also wide bandgap nitrides and oxides. P-type is usually hard or impossible, and even N-type, I mean, it can be challenging. I mean, it's not challenge to make gallium nitride N-type or gallium oxide N-type, but if you go to aluminum nitride or aluminum oxide, even that is a little bit tricky or not working. So understanding the compensation or the reasons for the N-type doping not working, it could be kind of interesting. So that's what we're doing. Okay, so compensation, quite often it could be vacancy defects, at least it could be. And of course, if we look at what we've done with positrons in the past, I mean, positron annihilation spectroscopy has been quite useful in identifying what is the main native acceptor defect when you n-type dope a semiconductor, or if you talk about nitrides and oxides. Gallium nitride is the gallium vacancy, indium nitride, the indium vacancy, zinc oxide, the zinc vacancy. Of course, nobody cares about compensation of n-type doping in these materials because there is no. But if you look at what is the main native acceptor defect that is formed when you do the n-type doping, it is the vacancy defect. In indium oxide, it seems not to be the indium vacancy, but this is a separate story. Now, when n-type doping becomes hard, then the question is that what happens in these ultra-wide bandgap systems? Are we still seeing that the main compensating or main acceptor defect would be vacancy defects, and if so, are they really compensating? And just as a reminder, for positrons in nitrogen and oxide, the general rules are that we can detect, identify, and quantify cation vacancies or metal site vacancies. Nitrogen and oxygen vacancies by themselves are pretty much invisible. Of course, we can identify complexes, but we can tell differences between metal vacancies, for example, metal vacancies and metal vacancies coupled with nitrogen vacancies, or more of them, or oxygen vacancies if we're talking about the gallium oxide system. So, now a couple of examples. In nitrides, we've studied nitrides quite a lot with positrons, and what we know is that, I'm not going through the details in here, but what we know is that in the binary nitrides, gallium nitride, indium nitride, aluminum nitride, the metal site vacancies really like to be present in complexes with something. In gallium nitride, they're typically complex with oxygen, if there's enough of it. With hydrogen, there's usually enough of it, or nitrogen vacancies. In indium nitride, almost always we see them as complexes with nitrogen vacancies, and usually actually with multiple nitrogen vacancies. There's plenty of that in indium nitride. In aluminum nitride, it would seem that in crystals of aluminum nitride, so bulk crystals, they're always with oxygen, and there's always enough of oxygen in aluminum nitride because, well, it's hard to get rid of oxygen in aluminum nitride. Well, maybe the MBE people are a different kind, but for the other stuff, this is what happens. So then, if you go to alloys, things get a little bit more complicated because now the SW plot, while it's kind of a simple thing to think about different lines in it, if you make an alloy, well, you have a gallium point that represents the gallium nitride and the gallium vacancy, for instance. And then you have aluminum nitride that is somewhere else in this plot, and the aluminum vacancy. And then, well, you end up having this, I don't know what it is in English, anyway, this sort of four corners, and the data points in principle can be somewhere inside. So you're not looking at linear behavior, but something that might be more complicated depending on the aluminum content, depending on the kind of vacancies. If you have a point here, it's very hard to tell what it actually says. So we have to try to do things a little bit more systematically maybe than in the binary compounds. Well, we've tried to do that. Well, there's a quick sort of showing that what kind of stuff you can imagine doing. This is now trying to understand silicon doping behavior in argon that has 90% aluminum, so almost aluminum nitride. What you get is that you have data points. For low silicon doping, you get a data point here, which is on the line between gallium nitride and aluminum nitride. Okay, fine. This is what you expect for an alloy if it doesn't have too many defects. When you start doping with silicon, now, you just dop them with silicon, the data points start moving along this line. There is increasing silicon. This is interesting. How did it go back that much? let's try to press the, oh, now it works. I'm too far. Maybe I should be here. Okay, so the data points start traveling to the right when you measure samples with more and more silicon in them. So you increase this means that you have more and more vacancies. However, if you look at the vacancy concentrations and compare them to the silicon concentrations, there's not enough of them to actually compensate. There's less vacancy effects than there's carbon, for example, in those samples. However, what you see here also is that the data points travel towards a vacancy-like point that lies on the line between the gallium vacancy and aluminum vacancy, but it's much closer to the gallium vacancy than to the aluminum vacancy, which suggests that the vacancies are actually in some gallium-rich surroundings, whatever that means in these algal alloys. At higher silicon content, the data points suddenly, when you reach a certain level of silicon, about 10 to the 19th, the data points start moving back. Actually, and not directly back, but actually back like this. This is the emergence of something we call negatively charged non-open volume defects or negative ions that are now in aluminum nitride-like surroundings because they are going to the aluminum nitride point here. And also, well, if you do some X-ray absorption spectroscopy, you see that actually silicon also does like this, that it seems to be in gallium-rich surroundings at moderate contents and in aluminum-rich surroundings at higher silicon contents. And there's no other impurities that have high enough concentration than silicon, so it really looks like that at high silicon content where the compensation kicks in these aluminum gallium nitride alloys, that silicon itself is the negatively charged defect. So maybe there's some sort of DX behavior. So you can try to understand things by following the points in the SW plot. That's what I'm saying here. There's a lot more details about this in Igor's paper about the topic. You can go and find it. This is from last year. It's kind of cool. But now the important thing is that why I want to discuss this a little bit more is that, of course, the answer to the question is that, well, depends on what mood you're in. Either say that, of course we do, or then you say that, are you kidding? There's something weird happening here, because if you look at these data points, we're talking about 90% algan. And the data point here is, well, it's, if you imagine maybe 90% algan, if you choose to believe in Vegard's rule, you'd expect the data point to be somewhere here, but it's here. Also, when you create vacancies, well, it would look like that this gets much, much closer still to gallium nitride, so way too close. So the question is, what's happening? We tried to understand this by measuring another series of samples where you tune the aluminum content, still at quite high aluminum content, starting from 60. And the data, well, first of all, you actually end up creating vacancies. Point being that what you expect is for this sort of set of samples that the data should follow a line like this rather than like this. So it's way too horizontal, meaning that whatever us seeing too much gallium nitride-like stuff gets worse with decreasing amount of gallium in the alloy. And well, there's some sort of overrepresentation. You can do the theoretical calculations. There is some overrepresentation, but there's natural because gallium has 10 3D electrons and aluminum has none. So gallium has much more electrons, positrons, and with electrons you expect a little bit of preference to gallium. But the effect is nowhere near the experiments. I mean, all kind of ways of getting, you put 10% of gallium in an algan alloy supercell, you get the data points here, which are a little bit closer to gallium nitride than you expect, while the experimental data point is here, that corresponds to like 30%. So we don't understand this. Let's see if in a year we'll know more. Example 2, oxides. Not any oxide, but the example would be beta gallium oxide. And the funny thing about beta gallium oxide is, in addition to it having a horrible crystal structure, it's monoclinic with quite low symmetry, 2 inequivalent gallium sites, making things complicated to begin with. In addition, theory says that the energetically most favorable gallium vacancy configurations are strongly distorted, which we call split gallium vacancies, where one of the adjacent gallium atoms move into an interstitial position, and you have like 2 half vacancies in there. And it actually gets even worse. People have calculated these sort of 3 split vacancies, which are part of the diffusion process. So it's a horrible thing. I mean, gallium oxide gives me a headache. Anyway, there's also experimental evidence of these split vacancies by many techniques, including ours. So positrons really also can identify these split vacancies, and actually it turns out that all bulk crystals that we've looked at so far of beta gallium oxide are full of these things, meaning that concentrations are well above 10 to the 18th. There's a horrible, horrible story. I won't tell you it in all details. However, it turns out that it's very difficult to study gallium oxide with positrons because of a strong inherent anisotropy in the Doppler broadening signals, which is something that is very unusual for a 3-dimensional crystal. And measuring in different orientations of the crystal, you get data points that are all over the place. And theories, and you can calculate this and you get the same stuff. I mean, this is not just an experiment, but also theory says that there's a match, that the huge amount of anisotropy between different crystal orientations is there. And what makes things difficult is that if you look at the SW plot in a standard setting for different kind of materials, you see a difference between the vacancy and the bulk point, or vacancy point and the non-defect point. It's big. But in beta gallium oxide, the full anisotropy for just measuring the defect-free case, if it existed, is larger than the difference between a vacancy and the sort of defect-free case, which makes interpretation horribly difficult, trying to understand what is going on. Turns out that you can actually use this anisotropy to your benefit a little bit and try to figure out what's happening. And actually, when we measure the bunch of aluminum gallium oxide crystals with different contents of aluminum and also with silicon doping, it turns out that we can see big changes taking place in this anisotropy. And we can tell that in undoped crystals, for example, we see just the split cases, and in these silicon doped, we see unrelaxed gallium vacancies, so meaning that there is a way of having these non-split vacancy configurations. Silicon somehow helps in it, aluminum helps in it a little bit. But just pointing out that this is a very complicated story with gallium oxide, but it also makes it very interesting. And the reason is that if you look at the positron state in these gallium oxide crystals, it actually turns out that it's not 3-dimensional. If you put a positron into this is calculations. If you put a positron into a perfect crystal of silicon or zinc oxide or indium oxide, you'll see that the positron density isosurface is all over the interstitial space. It's like a mesh. But in beta gallium oxide, it actually goes into this sort of tubular state along this. The gallium oxide crystal, if you look at it from a certain direction, has this sort of huge tubes, much larger than in silicon. And actually, it is this sort of non-3-dimensional positron state that causes all of the problems. And it is actually an inherent property of low-dimensional positron states, because this is something that was observed 40 years ago in graphite already. It's just that nobody thought about it for gallium oxide. Boron nitride is another example. There was a poster about it the other day, I think on Monday, where positrons also behave a little bit weird when you have a 2-dimensional positron state. So to summarize, see, I'm almost in time. To summarize all of this in a fairly brief way, I would say that even with all the difficulties, positrons are quite useful in trying to understand compensation in N-type doping, because we're creating acceptor-type defects, and positrons like acceptor-type defects. Not just in nitrogen oxides, in any semiconductor material for that matter. Trying to do this, identifying and quantifying vacancy defects that tend to be compensating defects is a good start. And in our case, we can determine concentrations in the range of 10 to 15th to 10 to 19th per cubic centimeter. I didn't speak about these details, but that is sort of the take-home message, if you wish. The situation is a little bit more complicated when you go to alloys, because of this, studying alloys is just difficult because, first of all, well, you don't have just one kind of vacancy. You have a gazillion type of different vacancies because the surroundings change. So they are not exactly the same. And maybe trying to analyze the local environment of the dopants, not just the vacancies, but now the dopants you're trying to use might be a key to understanding the compensation mechanisms. I mentioned that, suggested something about it in the case of aluminum gallium nitride, that silicon actually might be in different surroundings. This seems to be a little bit like this, maybe in the aluminum gallium oxide system as well. I said a few times that gallium oxide gives me a headache. Of course, just as a final note to all the PhD students here, the PhD student who studied gallium oxide was the first to study gallium oxide in my group and who figured out what's going on with the weird positron data. He put this post-it note on his box of samples. So if you're thinking of studying gallium oxide, just be sure that you know what you want. It might be tricky. Thank you.
Okay. Thank you, Philip, for nice presentation. I like both parts. First, here, Jaszowiec, and the second about effects too. Okay, so now it's a time for questions, comments. Yeah, please.
Thank you, Philip, for a very nice presentation. Okay, so I remember those times, still remember those times. Very nice. And I have a question concerning the so-called ideal crystal. You said that you can just theoretically predict something. Can you predict the properties of this ideal crystal, which is needed to study boron nitride, for example?
In principle, yes, but the problem with the theoretical calculations so far is that the approximations used are such that the predictive power for absolute data or absolute levels of data is still quite questionable. That's what I was showing. I showed normalized stuff, so comparing defect with the defect-free case. So then these approximations that you're using in DFT calculations kind of cancel out, or both in DFT calculations and in trying to how you actually treat the positron in the calculations. So what I'm saying is that the predictive power is not good for getting an absolute level to be able to say that, okay, we get this kind of data. Now this doesn't mean that this HBN sample is defect-free, or whatever that means. So no, not yet. There's work ongoing for this with developing QMC methods to have better absolute levels of predictive power, but this is maybe 5 years from now.
Okay. And anisotropy studies, do you think that it would bring some...
Sorry?
Anisotropy?
Yeah.
Anisotropy, okay. So
yeah. Well, that could bring something. I mean, but we're a little bit limited in geometry when we're studying thin films, because when you have the beam shooting to the thin film, we're measuring from the side. So, and the rotation in this is not the big anisotropy effect in layered systems. You would have to be able to measure from here and here to get this proper anisotropy. So I'm waiting for Isa and her team to grow big enough bulk crystals of HBN so that we can do that.
Thank you
no
very
pressure.
Much.
No, you need pressure, but
Okay, one more question. No more question. So thank you. Let's thank Philippe again, and I invite the second speaker, Carolina. Okay, Carolina Peret-Melessa, overcoming growth-related challenges in end-polar LEDs using plasma-assisted molecular beam epitaxy. So the floor is yours.
Hello, thank for kind introduction. I'm a second-year PhD student at Institute of High Pressure Physics, UniPress, Polish of Academy of Sciences, and I would like to talk to you about overcoming growth-related challenges in polar LEDs using plasma-assisted molecular beam epitaxy. In recent years, the free nitride groups such as aluminum nitride, indium nitride, and gallium nitride have become fundamental materials for high power and high frequency electronic and electronic materials, thanks to their wide and tunable bandgap, very stable and very high thermal and chemical stability, and high breakdown voltage. The main crystallographic structure of free nitride is the Wurtzite structure, in which we cannot obtain inversion of symmetry along the C-axis. So that's why we have clear distinction between nitrogen and gallium polarity. Most of the laboratories are doing the growth on gallium polar side of gallium nitride, because the growth on this side is more well established. And also on nitrogen polarity, we can see higher oxygen contamination and up to 40 times lower magnesium incorporation in the p-type layers. But even with these disadvantages, nitrogen polarity has a lot of opportunities, especially in case of long wavelength emitters. We observe enhanced indium incorporation, and even in molecular beam epitaxy growth, we can grow indium gallium nitride layers under nitrogen-rich condition in the same temperature as gallium nitride. Another advantage is related to the alignment of polarization field. As you can see in gallium polar LED, we have these potential barriers. So when carriers are moving toward the quantum well, they met this obstacle, which leads to lower injection efficiency and higher turn-on voltages. In case of N-polar LEDs, the potential barrier is on the other side of quantum well, and this leads to the reduction of the depletion wave and also lower turn-on voltages. In our group, we do all of the growth by plasma-assisted molecular beam epitaxy. This method enables us to obtain complicated set of super thin epi layers with high crystallographic quality. We use independent sources of pure materials, and as you can see, the materials are loaded in the fusion cells, which are mounted opposite to the substrate, and we control the duration of exposure time with swift opening and closing of the shutters. All of the samples grown on gallium polar side are usually grown in metal-rich conditions, but if we can translate this condition to N-polar growth. I wanted to answer this question with the graph. As you can see, with a slight excess of nitrogen, we obtain rough surfaces. Only when we increase excess of nitrogen above 50%, we can go to the morphology of meandering steps, and to obtain flat surfaces, we have to increase miscut angle from 0.5 to around 4 degrees. And also, I wanted to mark the usual condition for our N-polar samples. But knowing that, we wanted to see if actually in the structure we will obtain smooth layers, and we decided to measure the simple LED structure with narrow quantum well by TM measurement. And as you can see, there were no threading dislocation. And after zooming in, we can see that we have sharp interfaces between quantum well and quantum barriers. So the second problem that I mentioned was related to the higher oxygen contamination in the sample. So that's why we decided to measure samples with wide quantum wells by secondary ion mass spectroscopy measurements. This method provides us elemental depth profiles of the structures. The first structure was grown with the same condition as the one shown on TEM, but with wider quantum well. And the second one we grow in conditions similar to the gallium polar LED. And as you can see, in the sample grown under nitrogen-rich condition, we obtain even up to 10 times higher oxygen incorporation in quantum well. But what was more surprising, when we performed electroluminescence test, we saw that the sample grown under nitrogen-rich condition with higher oxygen concentration was the one with the better power output. The sample grown in metal-rich condition had barely measurable power output, as you can see over here. Okay, so now I explained to you and showed the differences between nitrogen-rich growth and metal-rich growth on n-polar substrate, but how we can compare directly n-polar nitrogen polarity to gallium polarity. For that, we have to reverse the structure of gallium polar LED by using bottom tunnel junction. And with that, we would have the same alignment of the polarization fields, and we can compare optical quality only in taking consideration the growth direction. We grew both samples in MBE. As you can see, both of them had flat surfaces. We processed them and we performed electrical characterization. The n-polar sample had a lower turn-on voltage, but we suspect that this additional penalty in voltage for gallium polar inverted LED was caused by bottom tunnel junction. Also, as you can see, n-polar sample had significantly higher carrier leakage in reverse bias, up to 2.5 volts. And there was large discrepancy across the points in this sample. That we suspect that it's because of the oxygen is non-uniformly incorporating in our sample and is partially leading to the passivation of the p-type layer in LED. Also, in higher current density, also both samples achieve higher current densities in similar voltages. This indicates that gallium polar inverted LED has lower differential resistance thanks to the contacts attached to the n-type layer, not the p-type layer as for the n-polar LED. Also, when we compare external quantum efficiency peaks of both samples, we can clearly see that the peak of n-polar, EQE peak of n-polar LED was located at lower current densities. And with that, we would think that n-polar LED would have better power output. But unfortunately, we couldn't be more wrong. For the gallium polar inverted LED, we achieved over almost 3 orders of magnitude higher emission. And we started to think why there is such a large difference in their power output, because as you could see, TEM measurement shown no dislocation, threading dislocation. The interfaces were sharp, and also we cannot blame oxygen as main problem with the power output, because as you could see in the SIMS measurement, the sample with higher concentration of oxygen was the one showing better power output. So we decided to dig a little deeper, and we sent a sample to Philip Tuomisto's group for positron annihilation spectroscopy measurement. For this measurement, we prepared 4 samples. 2 of them were grown on an n-polar substrate in nitrogen and metal-rich condition, and the other two on gallium polar substrate. And as you can see, in case of gallium polar samples, they are marked in yellow points. The nitrogen-rich growth resulted in a higher S parameter, which means we have a lot of more defects under these conditions. So we're expecting that. But in case of nitrogen polar samples, the results weren't this straightforward. As you can see, for both growth conditions, the S parameter was higher than for the metal-rich condition in gallium polar sample. And also, we could see slightly higher S parameter in gallium-rich and polar in the growth in gallium-rich conditions, and that would mean in this condition we have more defects. And to summarize, we show that N-polar LED are characterized by EQA peaks at lower current densities. In contrary to our expectation, contamination can be necessary to obtain power output in N-polar LED. And we think that by further optimizing growth condition, we can increase power output of our N-polar LEDs. And in parallel with the work which I presented, we want to obtain red N-polar LEDs. Thank you for your attention.
Thank you, Carolina. Yes, time for questions. Yes, please.
Thanks, Carolina. Very nice. Don't worry, I'm not asking you about positrons. But if you still go back to the S parameter plot. Looking at the gallium-rich R3, gallium-rich on N-polar, the blue squares, right? What I see there is that there's some sort of inhomogeneity as a function of depth in this sample. Not much, but a little bit. Do you see this kind of inhomogeneity in any other properties of these layers? Or any kind of inhomogeneity? Sort of starting from the surface, going deeper. Not here, but in other experiments. Do you see some inhomogeneity in other experiments?
No, we didn't see. And in TM measurements also, we didn't see any dislocation propagating from the substrate also.
Okay, interesting.
And what about indium? How many indium you have in quantum well?
Could you repeat?
How many percent of indium you have in quantum well?
In the quantum well shown in SIMS measurement, over here we obtained 22% of indium. And in the metal-rich grown quantum well, we had 27%.
Do you see some indium segregation to the top of quantum well?
In the TMs, we didn't see anything like that.
Maybe it's too thin, yeah. In order to have a segregation. Okay. Yeah. More questions? Yes, please.
Okay, thank you very much for a very nice presentation. I have a question concerning this oxygen, because usually you can see this, just if the concentration is very small, in the bound excitons in luminescence. And I wonder if you compare the samples, just with different parameters in this respect.
No, we weren't comparing that yet.
Okay, thank you.
Multi-junction quantum well electronic structure, could you please go to the... Yes, this one. We can see the bottom panel in the multi-junction electronic structure. The electron is moving up and the hole is going to this direction. So usually in physics, the electron go from the higher value to the lower value, but here it goes from the lower. So it is some barrier or it's some misinterpretation.
Like here,
in this one.
Over here?
Yeah, exactly. is there have some barrier for this electron to move from this multi-junction structure?
No,
or
this
it's-
barrier is because we have the alignment of the junction field and polarization field. So we, like in n-polar LED, you would have this potential barrier, and over here you have, like on the other side, because the structure is reversed.
Thank you.
Thank you, Carolina, for answers to the questions. Thank you for
Thank you very much.
presentation. And I invite the next speaker. So next talk will be given by Mateusz Haidel, entitled Full Elastic Relaxation of InGaN Nanopillars Grown on Gallium Nitride.
One, two, okay. Why it's no title here? Because it's here. Okay, thank you for this kind introduction. So today I'm going to present to you our recipe we got for a full elastic relaxation of InGaN grown on gallium nitride and why we need it. So we know all of this stuff that the gallium nitride use for the blue light emitters, right? They are quite nice operating, have a lot of applications actually for the laser diodes and LEDs, but the gallium nitride material family group actually have a lot of potential, and this potential is given on this plot. Basically, you've probably seen it already, but when you increase the indium composition, you can get whatever you want from the visible spectral range, right? And this is quite nice for some applications, and most of them are related to the display technology, right? So they have some augmented reality goggles. They have some specific requirements that would require us for producing the monolithic RGB emitter platform for this kind of applications. So this, when we see on the semiconductors which are available to do that, the gallium nitride is really the one to do it. And so we envisioned this kind of approach. So we want to produce this RGB micro LED matrix for those applications, right? And here we just combine the tunnel junction technology to stack different devices on top of each other, and with ion implantation we can produce the current path to supply and really supply current to the individual pixels of it. And with this approach we can have quite nice control over them, over the pitch and size of our micro LEDs here. So you can say, okay, you have everything, you can make it, right? But there's really a problem with the red emission from InGaN. You probably, when we speak about the efficiency of the semiconductors which emit lights, we talk about nitrides having nice efficiency in the blue spectral range, and green gap, we call it somehow green gap problem. But if the green gap is a problem for the nitrides, the red one is really a catastrophe. Because why is that? Because when you think about the monolithic approach, you most likely want to grow on your gallium nitride substrate, right? When you grow InGaN on the gallium nitride, indium gallium nitride is strained. So it shrinks in in-plane and elongates in out-of-plane direction. What it produces that you have some kind of critical thickness or composition you can grow on gallium nitride of InGaN to not introduce the defects. You don't want to introduce the defects, so you don't want to non-radiative recombination in your layers for the emitter, right? Second thing, which is more nitride related, you have piezoelectric polarization in this material, right? So when you grow the strained material, you actually end up with built-in electric field inside of the structure, right? So for the optical emitter, you use quantum well as your active region, right? So in the quantum well, when you have quantum well and then piezoelectric field, you separate actually the wave functions of the electrons holes, right? So this is so-called quantum confined Stark effect, and with that you have decrease of the wave function overlap, so decrease the oscillator strength basically. And as you can see here with the indium composition, it gets even worse and worse, so more of the separation of these electron and hole functions. And the third thing is that when you grow a strain material, you actually, your band gap of InGaN gonna increase slightly, right? So if you aim for the red emission, it's not also beneficial. So all of that somehow combines to the low efficiency of green and really poor efficiency of the red emitters made out of InGaN. So really easy solution here is remove this gallium nitride and just use indium gallium nitride substrate, right? But when you think about the monolithic approach, you want also your blue and green emitters, so you want to stick with gallium nitride. And the thing is that those substrates are not available yet, I mean, commercially, right? So it's quite difficult to do that. Quite difficult doesn't mean that people do not do it, right? So they kind of developed some techniques, and you can separate them into, let's say, big branches, most commonly used. So first one is use pseudo substrates, which is like partially relaxed InGaN layers, or on nanoporous gallium nitride is also developed here to produce such things, and they can show some nice EQE, nice, I mean, in terms of the InGaN and red emission for the 600 nanometers, and also the approach we was able to hear in detail on the Tuesday lecture from Professor Okawa. Actually, so you use pattern substrate and you use epi layer strain engineering to grow your InGaN layers, and you can get quite nice efficiency over here also. But the main conclusion from here is that the strain is really important thing when you think about the high efficiency InGaN layers. It was like asking ourselves what we can do. Can we really achieve complete relaxation of some composition of InGaN layers on gallium nitride? Because if we do that, then we can grow high indium content layers on the top without compromising any crystal quality. It means efficiency of the light emission, right? To increase that. So we was asking ourselves, can we completely relax our layers? So we did several things to achieve that. So first of all, we grow a thick indium gallium nitride layer on top of gallium nitride. We use plasma-assisted molecular beam epitaxy, and with this technique, we can, for the 8%, we can go as high as more than 1 micron actually, and we have perfectly strained structure of indium on top of gallium nitride. So over here is more or less 500 nanometers, 8% InGaN. So we are on the safe side here, right? So we have our strained InGaN layer here. Then the numbers here are really small, so I just enlarge them, and also here we have 18% quantum well on top to probe the optical properties and influence of strain to the optical properties. So when you want to relax the structure, you need to introduce the free space. So first, what we did, we etched nanopillars from 100 nanometers to 2 microns with help of our friends from Cesamat and Institute in Quebec. And with introducing the free space, the lattice can relax, right? But over here you can see we also have a special layer which I call sacrificial layer, because when you want to allow the lattice to really fully relax, you need to deattach it from the substrate. So we did it by introducing the nanoporous gallium nitride layer here using electrochemical etching technique. And just quickly with this technique, it's really selective to the doping level of your layer, and with the voltage and the doping, you can control really size and also the porosity of your layers, and you can even completely remove your layer from the device. So we did something like 20% porous. So we did like 20% of porosification. We did this. We used this over edge to introduce it to electrolyte, so it's going from the sides and porosifies the material underneath the pillar. Yes, and then we probe the strain. We use it for the synchrotron radiation, and we use the nanoprobe technique, which is developed on the beamline ID01. And this is basically just a scanning X-ray diffraction microscopy, but with the resolution lower than 50 nanometers. So this is really the best you can get. So in this technique, you're just basically scanning your sample, right? And for each point, you in 2 seconds get a full reciprocal space map of each point. So you scan this map several times, then you introduce some rotation, and then you can get 3D reciprocal space map of your sample. And then you change the reflection, and for several reflections, you can get full strain tensor, which will get you information about the strain state in your layers. So now coming quickly to the results, this is, for explanation first, I would use the gallium nitride peak, which should be simpler because it's gallium nitride on gallium nitride. So we're probing this kind of, let's say more or less this area of the sample here. It should not be strained, right? And if you see on the values here, actually they're quite low. So on average, there's no strain, but actually because we have a high amount of indium here, it actually also produces like an elongation out of plane of gallium nitride underneath the pillars, right? So we can see it here on the Z. This is X, Y, Z, and the asymmetric part of this matrix will be like rotations and bendings of the structure. So we see elongation in Z. Rest of the lattice have to correspond to that. Surroundings also have to correspond in that. On average, 0 strain in the gallium nitride on gallium nitride. Perfect. And now we're probing this relaxed InGaN part, right? So this is actually into the, this data here are shown corresponding into the perfect gallium nitride crystal lattice. So they are all looking like they are elongating, but actually what is happening, the InGaN wants to go again to this perfect InGaN crystal lattice, right? So it shrinks out of plane and elongates in plane. And on the axis, on the diagonal here, we see quite low anisotropy, which immediately tells us that there is a low stress in the material. And for this pillar, we can also, this is a 2-micron pillar, we can see that there is a higher strain on the edges of the pillar than in the middle, right? And then here from those asymmetric parts, we can also see that this movement happens, but also this kind of mushroomy bending stuff happening also here. And for the smallest pillar, we are able to measure, actually, we see more or less the same story, right? So really low anisotropy on this axis, but most importantly, we see that the most of the pillar now is highly relaxed. So we conclude that the whole layer is actually relaxed in this case when the pillar is small enough. So now we have to translate it to the crystal lattice. Basically parameters, right? So if we put it on the plot, we see that in C parameter, we see almost nicely reassembling our InGaN layers, now reassembling nicely fully relaxed InGaN 8%. And also for the A, we see a bit of, let's say, over-relaxation, which we think is because we have this quantum well on top also of higher indium content. But most importantly, we achieve this fully relaxed 8% InGaN on the nanoporous GaN pillars. And now we have a quantum well, which is strained not to the gallium nitride, but to this 8% InGaN, right? So we want to probe we can use it as a separate probe of the strain actually and what is happening with the device. And here's the result from the middle of those pillars, right? So here was high relaxation in the smaller pillar, in the whole area of the pillar, and on the biggest pillar, the middle was less relaxed, and we can actually see that. So we have a blue shift corresponding to the non-strained signal, right? We have a blue shift in both cases, but here the blue shift is a bit higher. So I was happy really with that, maybe not in terms of getting the red emission, right? But it tells us something about what is going on. So we have actually competition about the two factors. The quantum confined Stark effect, we're decreasing it with decreasing the strain, and the band gap change should actually work opposite. So it should produce the red shift. We see blue shift, so we can conclude that the decrease of the quantum confined Stark effect is superior here in this case. And with that, I would like to end and just maybe like a home message for you. We just know how to get full elastic relaxation of 8% INGAN, and now we kind of open the new way to think, okay, what is the critical thickness? Maybe we can, how much composition, how much thickness of this layer we can introduce to get these materials and study it more. Okay, thank you.
Thank you, Mateusz. Okay, so we have a time for one small question. Yeah, please.
Thank you very much for your talk. Nice results. My question is, you showed us shift of PL as a result of relief of strain. That's obvious. What about intensity? What happens with intensity when you do etching? Because it's known that in this top-down approach, there are many defects in the side walls. Did you try wet etching after this process, or eventually overgrowth? Or that's my question.
Yeah, so here we studied it in the middle. Of course, for the smaller pillar, I do not have a data right now to show the intensity difference. This is normalized here, right? And the peaks here. We do not see in the middle difference between those signals of the unstrained and strained material, right? Here. What?
Surface matters for narrow pillows, yeah? So for large ones, you do not.
Yes, yes. And yeah, we did re, and after that we did now also wet etching here in this case.
Okay, one more small question.
You talk about strain the volume. I was wondering, what about surface? Does it introduce non-dilatative channels over combination?
I mean, surface on the sides of the pillar?
Walls, yes.
Yes, they will be. They will be the intensity on the intensity basically of the PL on the edge of the pillar will be is much lower, yeah, than in the center. But I mean, it's always happening when you do the etching of the sides. You do not protect it anyway, right? To the final design of the RGB matrix, we are not sure we're gonna use this approach, this specific approach, right? We more use it as a probe, what we can do with the strain and how we can get nice emission, red emission, and then we can implement that to the final design. In the final design, we do not have edge. We have doing with the ion implantation, right? So it's slightly reduced this combination over there.
Okay. Thank you. Let's thank Mateusz again. Yeah. And I invite the next speaker, Marta Chabowska, again about the nanopillars, very interesting topic. So, defect-induced shape selection in nanopillar formation.
Thank you for introduction. Today, as it was told, I will be talked about different shapes and nanopillars, which are formed due to broadly defined defects. Okay, shapes. So when we think about shapes, I think the best former of the shapes is the nature. Nature creates steps or step bunches, different shapes of meanders, mounted structures. It also creates pillars, wires, and various fractal structures. But people are not worse. We also form beautiful different shapes like pyramids, like micropillars or mounded structures, meanders, step bunchers, or some fractal dendritic structures. In our group, we model all of these structures, but today I will focus only on those. For simulations, we use a vicinal cellular automaton model, which consists of two different modules. The cellular automaton one, which is responsible for the description of the growth of the crystal, and Monte Carlo part, which is responsible for the description of the diffusion of atoms on the surface. Our model consists of two-dimensional vicinal or flat surface. Above to it or attached to it, we have an additional one-dimensional layer with randomly distributed atoms. Above to it, we apply the surface potential energy, which senses these diffusing particles. Then we define the cellular automata rules according to which particles will build into the structure. And at the end of each simulation step, we compensate the number of these diffusing particles to its initial value. There are three situations which we consider when we are thinking about incorporation of particles into the structure. The first one, when the incoming particles is located in the king position. In this situation, these particles are incorporated unconditionally. The second situation is when the incoming particles is located next to the straight step. In this situation, the particle will be incorporated into the structure only when in its vicinity there is an additional particles. And the third situation is when the nucleus is forming on the terrace. And we assume that these particles, the nucleus will form when there are four particles next to each other. Okay, we have this surface, we have diffusing particles on it, and the source of different shapes which occurs in our simulations arises from the interplay between the dynamics of these particles and the interactions between these atoms. These interactions determine how particles move on the surface. And these interactions, in our model, are represented as the surface potential energies. And the advantage of our model is that we can modify these surface potential energies according to the situation occurring at the surface. That means that we can include everything what occurs, each defects, the absence of these defects. What is also important, this surface potential is not constant during the growth. It changes together with the evolving surface potential. In our simulations, particles diffuse independently and with the probability given by this formula. On the flat surface, they diffuse with equal probability, while in the vicinity of the step surface, it's modified by the presence or absence of barriers, potential wells, which appears due to the step presence itself or dangling bonds, etc. Today, we are interested in the surface with a defect on it, and we assume that this defect is a source of potential which propagates as a 1/r² across the entire structure. This such defined potential, and after the analysis, it's turned out the most important in this analysis is the probability of a datum attachment to the king position and to the straight In our model, the probability of attachment to the king position in case of hexagonal structure means that we are attaching to the 3 atoms is given by the exponents of a certain value. Probability of attachment to the step is the squared probability of this attachment. Okay, let us assume that we have low probability of attachment to the structure. Then we finish with shape which symmetry is consistent with the symmetry of the substrate. When we increase the probability of attachment, it means that more particles are joined or incorporated into the structure. Then the final pillar will have the symmetry which is independent on the substrate orientation. Further increase of this probability leads to the structure which cross-section is also hexagon, but it's twisted with respect to the substrate orientation. Okay, we have the model, but are we close to the experiment? Let us start with the structures obtained from cadmium selenide layers in PVD techniques. As you see in experiments, Lewankoy obtained beautiful pyramids. Okay, our first shot maybe are not very as beautiful as experimental, but at least we are close with such shape. When we start to simulate, consider this only one structure on the substrate, then we finish with beautiful hexagonal pyramids. Next, we were asked to simulate the structures obtained on thin selenide flakes obtained by an SSVG technique in the group of Michał Schott. And among these various structures, such beautiful spiral pyramids were obtained. With our model, we are able to obtain also such structures with spiral defect in the center. Okay, but SSVG is the process which the structure from which it shows that the growth occurs due to the temperature gradient, which causes that particles from the source goes to the substrate. Then it's on the substrate, of course, at some moment nucleus is formed, and such nucleus also form the steps. And this in this step is a source of local changes of the interactions occurring at the surface. So we modify our model in such a way that we take into account that step, we have this temperature gradient which causes the upward flow of the particles. With such modified model, we are able to obtain our structures. We are able to obtain similarly as in experiment with conical micropillars with circular base and apex, also the hexagonal structures, as well as the micropillars which base is hexagonal and the apex is circular. In this process, the source of these different shapes is the temperature. When the temperature is higher, then these effective barriers at the surface become smaller. Together with that, it means that if higher temperature, more particles is coming to the structures, but this also means that less probable is that particles will be incorporated into the structure. Okay. To conclude, using our vicinal cellular automaton model, we demonstrated that the way the particles interact with the surface determine the shape of the final structure. When we consider the potential which is induced by defect, and it's a global one, then we obtained three-dimensional micropillars with the symmetry which is largely independent of the substrate orientation. Local interactions means that we finish with structures which symmetry is consistent with the substrate, but which, when we include the temperature gradient, then this gradient significantly impacts the shape of the structures. With that, I would like to thank you, the experimentalists, for sharing their results, and you for your attention.
Thank you, Marta. So, time for questions, comments. Yes, please.
Thanks for the interesting talk. I have a question regarding the way this is modeled. So do you consider only single kind of element or both kinds of elements for the
At this moment, a single type of atom, but we are in the process of switching to two type of particles.
Got it. So this all was done with single, and still you could reassemble
Yes.
the same structure. Thank you.
More questions? Yeah, please.
Yes.
It was prepared, yeah, the answer was prepared, okay. And more questions? So I would like to continue this question. Is it possible to grow only pyramidal type pillars, or how to say, pillars, not pyramidal, but
yes.
rod type?
Yes, rectangular, but much broader, much higher, yes, it is possible. Also wires.
Oh, nice. And how high these things can be?
Okay, it depends how long we run the simulation.
Oh, okay. It doesn't depend on the experimental part, yeah?
Okay, we can, not, maybe not yet, but we're not connected with that, but somehow we can estimate it.
Okay, thank you. If no more questions, let's thank Marta again, and I invite the last speaker. Okay, Lena Miller, and the title of presentation, Anomalous Temperature Behavior of Hydrogen Complexes in Epitaxial Boron Nitride.
Okay, thank you for the kind introduction. Good afternoon. I hope you can hear me loud and clear. And I'm very grateful to speak in front of such a noble audience. Today, I would like to give you an insight into hydrogen complexes in epitaxial boron nitride. So, let's start with the main motivation of our project. So, the long-term goal for our project are quantum sensors. Such sensors are based on spin defects, and by moving these sensors over the surface of some probe sample, we are able to measure some specific factors of the sample, such as magnetic field. Contemporarily, these sensors are usually based on a nitrogen vacancy center called NV center, found in a diamond crystal. However, diamond has a three-dimensional nature, and it's a huge disadvantage because it limits the obtainable proximity between the probed sample and the tip of such sensor. This means that we need to step up and we need to find a better solution, probably to use a two-dimensional material, which has almost a limitless proximity between the probed sample and such sensor based on a two-dimensional material. Here on this schematic picture, you can see how such sensor would work. So the gray planes indicate atomic layers, while the arrows are the spin defects. And when there is a local shift in some factor, for example, magnetic field, we can detect shift in the resonant frequency of such spin defects. A prominent example of the two-dimensional material that we could use instead of a diamond could be boron nitride. Boron nitride is a host for a spin defect that is called negatively charged boron vacancy. And from the ODMR spectra of this defect, comparing them to the ODMR spectra of the envy center found in a diamond, you can conclude that in fact it could be a substitute for this spin defect. And it was actually shown before that we can use boron nitride in our quantum sensors. Here is an example of the magnetic field mapped of the sample of chromium deuteride, and it was mapped using the quantum sensors, which was based on the boron nitride. Our samples are grown using metal-organic vapor phase epitaxy, which is an epitaxial method that allows us to embed atomic layers onto the chosen substrate. In our case, we use the reaction between triethylborane and ammonia to embed our layers onto the 2-inch sapphire wafers. Then those layers can be easily exfoliated in the water, and they can be equally easily transferred to the desired sample simply by fishing this foil with the sample we would like to probe. However, the main question here is how exactly can we create those vacancies, those desired negatively charged boron vacancies in our material? Well, on the level of the growth process, it is pretty difficult to achieve the material that would get the high concentration of those defects. This means that we should use other methods, and one of these methods is thermal neutron irradiation, in which we bombard the surface of the sample with thermal neutrons, and it causes our desired defects to emerge. Now I need to stress one important factor that is crucial for our project, that natural boron nitride is composed of 2 isotopes of boron, boron 11 and boron 10, around 80% of boron 11, and of course the rest of 20% of boron 10. Boron 10 is characterized of an outstanding thermal neutron capture cross-section, which is at the same time 3 orders of magnitude higher than the cross-section of B11. This means for us that if we had an isotopically enriched boron nitride that would contain mostly that isotope B10, we would be able to create our material with high concentration of our desired defects, and at the same time a low risk of damaging our material. Now you would probably like to ask me, so what is all this fuss with hydrogen that I placed in the title of this presentation? Now I will ask this question. So boron nitride is the host for a wide range of many various defects, including complexes that are hydrogen related. Unfortunately, when there is hydrogen present in these complexes, it can passivate other defects. It can reduce their efficiency, including our desired negatively charged boron vacancy. And it was actually shown using photoluminescence measurement. As you can see here, after the annealing procedure done on the samples, we can see that significant increase in the signal from the samples comparing to before. This means that hydrogen was reduced from the samples and it stopped passivating our defects. This means for us that it is crucial for us to investigate those hydrogen complexes in boron nitride for our further findings. Okay, first of all, we have done Raman spectroscopy measurement on our samples. As you can see, for the natural boron nitride sample, we can observe a very characteristic of boron nitride peak around 1,371 over centimeter, which of course can be ascribed to the vibrational mode of boron nitride. Then there is one important effect that for the isotopically enriched samples, this peak is shifting to higher energies. How can we explain this? Using the simple theoretical model of spring and balls and using the formula for the frequency of the spring. Now, if we assume that in our lattice, we exchange these atoms of isotope B11 for isotope B10, we can see from the formula that actually our reduced mass drops, which increases the frequency of this vibrational mode. And from the result of this calculation, we can see that they are in fact in a good agreement with what we see from the Raman spectroscopy. Secondly, we have done optical absorption of our samples. And I would like to draw your attention to those two specific absorption peaks. One was observed around 3,200 centimeters, and the other one around 3,400, around 31/30 meters. Why? Because they were observed around in the range when we usually observe hydrogen-related complexes. Now, what is most important here is that we see a shift between the vibrational energy for the peak, for the sample with the natural bond nitrate and the sample that was isotopically enriched. So this means that this peak could be ascribed to some complex, including boron atom. And what is even more important is that it cannot then contain any boron vacancy, right? At the same time, we would like to verify whether, in fact, our samples our peaks can be attributed to anything hydrogen-related. So we submitted our samples to the annealing process. And as you can see, comparing the results before and after annealing, we can see the significant drop in the signal after annealing, which means that, in fact, we can probably ascribe those both absorption peaks to some hydrogen-related complexes. To investigate our samples even further, we have done temperature-dependent optical absorption of our samples. First of all, you can see that for both the natural bond nitrate as well as the isotopically enriched bond nitrate sample, this lower energy peak is shifting to the higher energies, the higher values of energy with increasing temperature. However, for this higher energy peak, we see that it's completely insensitive to any changes in the temperature. So to summarize those last two slides more qualitatively, we can see that for the higher energy peak, there is no shift in energy with increasing temperature, and as well the vibrational mode, vibrational energy of this mode is almost the same for both samples, regardless their isotopical enrichment. However, we see two important effects for the lower energy peak, which is, I think, more interesting. First of all, it's shifting to higher energies with the rising temperature, and also we can see that isotopical shift, right? However, how can we explain this shifting to higher energies? A bit of theory. So for the typical three-dimensional crystals, when the temperature is rising, the crystal expands and it's increasing the distance between our atomic orbitals. So actually we are lowering the vibrational energy. However, in the two-dimensional materials, we observe something called a phenomena called anomalous thermal expansion. So in the out-of-plane direction, the crystal expands the same way as the three-dimensional crystal. However, in the in-plane direction, the crystal lattice actually shrinks, bringing those atoms closer. And we observe a shift to higher energies with the rising temperature. This can explain how our peak is behaving. So it should be attributed probably to some mode that is placed in the in-plane direction in the lattice. To summarize all of our results, first of all, what we saw after the annealing procedure is that we now have a proof to attribute those two vibrational modes to some hydrogen-related complexes. From the temperature-dependent spectra, we can see that the lower energy peak is shifting with the isotopical content of our samples, as well it's shifting to higher energies with the rising temperature, which wasn't seen for the higher energy peak. And also from the anomalous thermal expansion of two-dimensional materials, we suggest that this lower energy mode could be ascribed to some complex including both boron as well as hydrogen atom, and it's moving in the in-plane direction. And right now, I assume everyone is very hungry for the group photo, so thank you for your attention.
Thank you, Lena, very much for nice presentation. So we still have some time for questions. Yes, please.
Thank you for a very nice talk. I'm curious if you have tried maybe to determine the structure using neutron diffraction or electron diffraction, and maybe are you going to do it in the future? Because we can map the position of hydrogen atoms in the structure and determine what kind of complexes you may have in detail.
Yes, so this is actually a very good point. We haven't done it yet because this project is, as you saw, very huge. So we are in the middle of some steps, but I think it will be a step for the future.
Thanks a lot.
Okay, more questions? Yes, please.
Thank you for the very good presentation. I was wondering just about the anomalous expansion. So is it because it's a 2D stack, or a single layer also, a single 2D layer also has this anomalous expansion?
Can you repeat? Sorry.
So you explained that the distance between the layers grows with temperature, but
Yes.
the lattice shrinks.
Yes,
And
yes.
Does it happen also for a single layer, or it's
For a single layer?
Yeah.
Well, it's for the further verification then. Yes?
Thank you. Okay, if there is no more questions, so I would like, and you would like, to thank all speakers again. Philippe, Carolina, Marta, Mateus, and Lena, and now a short announcement from organizers. Yeah, please.
Thank you so much. So again, the reminder that we are taking a picture just in 15 minutes. And the other announcement or reminder is that the presentation, which was supposed to be held today at 2:30 from a fintech company, it was cancelled. So please remember that you don't go there. Thank you very much.
Okay. Yeah. Hello, Param, are you there? We are ready to test your presentation. Could you share a screen with me?
Okay.
One moment, I do not hear you. One moment, I need to change something. Not this one, Krzysztof, the other. Yeah, the input from the Zoom. Yeah. Could you tell something for me? I do not hear you. You have a mute. You mute your microphone.
Okay. Right now it's fine.
Okay, I do not hear you. Sorry. Yeah, I mean, I hear you not very well. It is a very. You need to increase your volume.
Okay, now it's fine.
Give me 1 minute. If I have everything on Mac, I will check my. Okay, here is a maximum. Yeah, this is maximum.
Okay. Now is it fine?
No, 1 moment. I really have a bad voice of. Okay. Let's try again. Say something.
Yeah.
Just continuously speak, yeah? I will try to get a...
Okay. I mean, things are
Yeah,
okay now.
more?
Okay.
No, you need to change something. It is on your side, because I have everywhere maximum volume, and I can still do not hear you on this audience. This hall is large, yeah? You need to change mic, I don't know.
Right now it's fine?
Oh, now it's much better. I will move the camera
Okay.
that you will see me.
Okay.
You see the hall is quite large.
Okay. Yes. So I think, can I share my screen?
Okay, 1 moment, I will put a... Przepraszam, mam teraz... Czy coś... Jeżeli coś pilnego, za 10 minut, dobrze? Okay, sorry, this... Okay, you will see also as a feedback our screen.
Yes.
That you will also see the presentation, how it looks like on hall. Okay, I'm just doing a zoom on the camera. Yeah, you see the announcement at the moment.
Yes.
Okay, please share your screen with me.
So I think you need to stop sharing other one, then only I can share.
Okay, I will stop sharing my screen. Yeah, sorry, I forgot that I lock it. Main current size. Okay, 1 moment. Stop. Okay. Okay, stop sharing. Okay, now probably now you can.
Now I can share.
Okay. Give me
Now,
we are almost there. Give me 1 minute. I need to move the window to the right position. Make it full screen. Okay. Share your presentation.
yes.
Start the display, and we'll check. Okay.
Is it fine now?
Yeah. Do you have a better mic? Because it's really... you are using a mic from the laptop, yeah?
Yeah, I'm using...
Now, okay, you need to be just closer to the laptop. Now I hear you. You are too far from the laptop.
Okay, okay.
Okay.
So,
The hall is almost empty, then you can try. I will just see. Okay? Just start, just display your talk once again. Change the mouse to the pointer that we will see what you will show us. Yeah, make a, yeah. Okay. It's working now. And remember, put a laptop close to you, yeah, because we will be not able to hear you, especially if here will be more people or the audience, yeah.
I think now it's fine, right?
Yeah, now when you are sitting like this is fine. It's perfectly fine, yeah.
So,
okay. Do you need any other assistance for me?
No, I just want to see that one video it's playing properly or not. Just okay. Is that video is playing properly?
Yeah, we see it doesn't change as smoothly because this is a properties
Yeah.
of the zoom, unfortunately. But we see it change. Yeah, it is like in the old movies, frame by frame. Yeah, but
Yes,
it's
yes,
not
yes. It's
it
like
is
that.
not a continuous. Yeah. Okay,
Okay.
we
Okay.
see it.
Okay.
Every
I think
some. Okay.
then it's fine from my
Okay,
side. I just
you can change these properties if it is a smooth animation. You can change these properties by there is a kind of movie option in the Zoom when you are share the screen. I do not remember where is this option, but you can look for it. If not, it's still fine.
okay. 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 Then I think from my side it's okay. So just so at the presentation day, automatically I will be notified, or just like I'll join there when my
Join on the beginning at the beginning of the session because I will prepare then everything for the display that the transition between the speakers will go smoothly. Yeah, just because you are speaking as a second one. Yeah, I could
yes.
remember.
Yes. Yes.
Yes, you are speaking that. Be ready. Let's say 10 minutes before the session. Please connect. We will check once again if everything is fine, and then wait for your time. Okay, without any okay with some changes because I need to share the screen from the first speaker. Yeah, because this is a remote conference. There are also other attenders, and then you will share after the second speaker. You will share your screen. Okay.
Okay.
Okay. Then have a good day.
Okay. Okay. Thank you.
Tu już poszły bakterie, poproszę. Raz, raz, raz. Sprawdźmy, czy tutaj słychać. Słychać, słychać. Ja dam go na full screen, bo zupełnie nie wiem, czy nie będzie jakichś, wiesz, przemówień zdalnych. Tego mi nikt nie powiedział. Tak. Tak. Poczekaj, tylko zrobimy. Ja zobaczę, jak się robi full screen. Przełącz na mnie na chwilę. Dobrze. Sprawdźmy jeszcze.
Raz.
Dobra, i teraz jesteśmy online. Ja już, żeby się nie mieć wpadł.
Ladies and gentlemen, good evening. Well, we arrived to the middle of the Jaszowiec conference, and that means that we have a conference banquet tonight. So I would like to welcome you heartfully together with Anna Kafar here. And well, this is usually, you know, you are sitting at the table waiting for the beginning of the dinner, but we have this maybe not a hardship before we start, but somehow also a pleasant moment, I would say, because this is also a time when we inform you and also inform, let's say, the most interested persons about the results of poster competition. Yeah, we have, as usual, we have a best poster competition, and we have the results. So I would like to congratulate all students, mostly students who participated in this contest. And I must say personally, I looked maybe not at all, but at the most of posters, and they were really good. I mean, you spend a lot of time preparing them, and well, the program committee, maybe extended program committee, voted and rated your posters, and the results are as follow. And yeah, and I would like, which is very important, that the prize for best poster award was funded by Eurotech company. So yeah, so the best poster award, the first winner is Emilia Ziemba-Ostuj for the presentation Electrical and Optical Tuning of Telecom Band Indium Arsenide, Indium Phosphide Quantum Dots using a non-local biasing scheme. So Emil. Yeah, so this was the first winner, and the second winner is Joanna Duchna. Congratulations. And the title of the poster was Refractive Index Engineering in Porous Indium Phosphide for High Contrast DBRs. Photo. And well, to be on the equal side, we have one boy also getting the prize. So this is Grzegorz Krasucki for the poster entitled Thank you. Thank you very much. Congratulations. And the next part of this, let's say, official part of this evening is equally pleasant occasion, because this is also the question of prize and winners. And in this case, this is Leonard Sosnowski Prize. So basically, I will pass the microphone to Professor Kosacki, who will tell you about the details.
Okay. Good evening, ladies and gentlemen. It's my great pleasure to be here, and as I have honor to chair the commission for the Leonard Sosnowski Prize, I can announce today evening the winners of this prize. But before doing that, I would like to say a few words about the prize and about the person to whom this prize has its name. So Professor Leonard Sosnowski was the founder of the School of Semiconductor Physics in Warsaw at University of Warsaw, and later in Academy of Science, Institute of Physics, Polish Academy of Science. And in general, he was somehow founder of the semiconductor physics in Poland. So he was very important person not only in organization achievements, which were establishing this community, but he was also a very active supervisor of students, and he had numerous students and people who he shaped the community of semiconductor physics. And in the middle of or beginning of 90s, when there was very difficult economic situation in Poland, former students of Professor Leonard Sosnowski, which were abroad, decided to found the prize for the student to help him to prepare Master of Science degree at University of Warsaw. And this was for the student after fourth year of studies, so the last year. And it was for someone who is preparing thesis in solid state physics, theory or experiment. And this prize was founded by our former students of Professor Sosnowski, which were abroad, but since 2010, this is founded by physicists from semiconductor community in Warsaw and other institutions in Poland, as well as physicists from abroad and all people who are somehow related to the Warsaw School of Semiconductor Physics. And since 2021, the prize is also not only for students, but also for PhD students. So there are two categories. One is for student at Faculty of Physics, University of Warsaw, and the second one is for the third year PhD student in any institution in Poland. And a unique feature of this prize is that it is founded not by institutions or companies, but it's founded really by the members of the semiconductor community in Poland and abroad. So there are only individual sponsors who are collecting money for this prize. And this is really value of this prize, because this is quite unique, that it shows that we are really one community responsible not only for the research, but also for shaping and helping our younger colleagues. So this is really something unique for me. And here I would like to thank Professor Maria Kamińska, who is taking care of collecting money. So it's very important function in this prize. And probably we should proceed to announcing winners. But before I announce, I have one more remark, that as I'm working as a professor at university, so it happens that I have students. And sometimes they are really very clever and very good, and they are not punished because of that they are my students, so they can apply for this prize. And if they apply, then I, of course, do not participate in discussion and voting. I'm just taking care of organization, and this was the case this year. So for the students, I was not involved in the decision, but for PhD student, I can participate fully in the work of jury. So let me proceed. So a history of the prize and the list of sponsors, which is the very important part of this prize. And the first is the Best Student Award, and this year jury decided to give one honorable mention to Zofia Bedyńska. And the winner is Maximilian Kuna. And traditionally, this we can open this one, yeah, because it's since the beginning, the laureate is getting such plaquette which is made of silicon. So be careful not to break it. Okay. And the second category was a PhD student, and here jury had quite tough work, so again decided to give honorable mention, and the honorable mention is to Karel Olszewski. And the winner is Gayatri. Congratulations. Thank you. So, that's all. I would like just at the end thanks the sponsors and the founders of this prize. Thank you.
You had a really pleasant moment, and we have many winners, and well, it's very optimistic to have that many talented young people among us. So congratulations once again to all the winners. Coming closer to the end of this official part, I would like to acknowledge and thank the company Laser System Integrators for providing us this evening wine. So yeah, that will be really enjoyable. And I would like to also to thank once again Józef Dresner and company Euratech for Best Poster Award prizes. So thank you very much. Thank you all sponsors, and enjoy the evening.